The moment the object first appeared in astronomical data, it did not announce itself as a crisis. It looked, at a glance, like yet another luminous point among millions catalogued each year. The initial detection came from a deep sky survey conducted using the European Southern Observatory's Very Large Telescope in Chile during a routine sweep of a dense stellar region near the outer edge of the Large Magellanic Cloud. The survey's primary goal was to refine distance measurements for massive stars in low metallicity environments and to update luminosity calibrations for known stellar populations. What the instruments captured instead was a source whose brightness and spectral behavior immediately exceeded the expected range for its apparent distance. If you're intrigued by the extremes of the cosmos, this star will challenge everything you thought you knew. It shone hotter, brighter, and stranger than any star ever recorded, defying the rules of physics. Astronomers scrambled to verify it, and every test confirmed the same impossible truth. This star should not exist. Subscribe now and join us as we uncover the universe's most astonishing mysteries. At first, the anomaly was treated conservatively. Automated pipelines flagged the source for follow-up because its recorded apparent magnitude implied a luminosity comparable to the most extreme stars known, yet the distance estimate placed it far from any active star-forming region. The first suspicion was instrumental error, possibly caused by detector saturation or atmospheric distortion. Engineers reprocessed the raw frames, recalibrated photometric zero points, and compared the results against reference stars in the same field. The anomaly persisted unchanged. When the data were cross-checked against archival observations from the Hubble Space Telescope, the situation escalated. The object was found to have been present in deep field images dating back at least 15 years, showing a remarkably stable brightness across multiple observing campaigns. The consistency ruled out a short-lived outburst or transient amplification event. This immediately raised concern, as stars emitting at such inferred energy levels are expected to show violent variability, episodic mass ejections, or catastrophic instability on much shorter timescales. Within weeks, independent confirmations arrived from the Atacama Large Millimeter, Sub-Millimeter Array, and the Gemini South Observatory. Each facility examined different portions of the electromagnetic spectrum. Infrared observations showed no excessive dust shrouding that could artificially inflate brightness measurements. Ultraviolet spectra revealed ionization levels typically associated with far hotter or more compact objects. All instruments converged on the same conclusion. The source was neither transient nor exotic in the usual sense. It behaved like a star, yet it emitted more energy than stellar physics permits for its inferred characteristics. By the time the object received its provisional catalogue designation, internal discussions within astrophysics departments worldwide had intensified. Researchers from the Max Planck Institute for Astrophysics calculated preliminary radiation pressure estimates and found that, under accepted models, the outward force should have exceeded the star's gravitational binding by a substantial margin. In such cases, stars are expected to drive extreme stellar winds or eject entire outer envelopes. Observations showed no such evidence. No surrounding nebula, no expanding shell, and no significant enrichment of nearby interstellar gas were detected. The object appeared compact, sharply defined, and structurally intact. The first peer-reviewed paper addressing the anomaly was submitted less than 3 months after confirmation. It deliberately avoided interpretation and focused entirely on measured quantities. The authors reported a bolometric luminosity exceeding 10 million times that of the Sun, a value that placed the object well beyond the accepted upper boundary for stable single-star configurations. Its spectral classification resisted assignment. It shared some traits with luminous blue variables, yet lacked their instability. It displayed emission features reminiscent of Wolf-Rayet stars, yet its inferred surface temperature did not align with that category. As awareness spread, alerts circulated through the astronomers' Telegram network. Observatories across multiple continents coordinated follow-up campaigns. NASA's Chandra X-ray Observatory detected persistent high-energy emissions without the sporadic flaring normally associated with extreme stellar mass loss. The signal was steady, suggesting a sustained internal process rather than episodic events. Meanwhile, the Fermi Gamma Ray Space Telescope recorded no statistically significant gamma ray activity, eliminating scenarios involving compact object accretion or hidden relativistic jets. One of the earliest and most critical verification steps involved distance measurement. The European Space Agency's Gaia mission provided parallax data precise enough to settle lingering doubts. The distance uncertainty was reduced to less than 2%, eliminating the possibility that the luminosity estimates were inflated by misplacement. The object was not closer than assumed, nor was it a background source magnified by chance alignment. It occupied exactly the region of space indicated by the original survey, and its brightness was intrinsic. The gravity of the situation became unmistakable during a closed workshop held at the Kavli Institute for Cosmological Physics. Specialists in stellar evolution, radiation, transport, magnetohydrodynamics, and plasma physics examined the data collaboratively. Each discipline attempted to reconcile the observations within existing theoretical boundaries. Every attempt failed without violating at least one well-tested constraint. The star was simultaneously too massive to be stable, too luminous to retain its structure, and too persistent to represent a fleeting evolutionary stage. What unsettled researchers most was not only the star's extreme parameters, but its apparent normalcy. There were no precursors of collapse, no expanding shock fronts, and no erratic pulsations. Long-term photometric monitoring showed variations consistent with surface phenomena rather than global instability. This behavior stood in direct contradiction to decades of observational evidence, showing that stars approaching theoretical limits exhibit increasingly chaotic signatures. The object's galactic environment compounded the mystery. It resided in a region characterized by relatively low metallicity, meaning a scarcity of elements heavier than helium. According to established theory, such environments limit the formation of extremely massive stars because reduced opacity alters radiation-driven mass accumulation. Yet this object's inferred properties suggested a mass well beyond those limits, forming or surviving where it should have been suppressed. Predictably, skepticism intensified. Some researchers proposed that the star was actually a compact cluster of unresolved stars. High-resolution interferometric observations quickly dismissed this. The light profile remained singular, even at angular resolutions, capable of separating objects only a few astronomical units apart at that distance. Others proposed gravitational lensing, but detailed lensing models failed to reproduce the uniform spectral amplification observed across wavelengths. The turning point came when theoretical astrophysicist Elena Markovich presented an analysis demonstrating that no equilibrium solution within standard stellar physics could sustain the observed luminosity. Even when assuming unusually efficient internal energy transport or reduced opacity, her models predicted rapid self-disruption on timescales far shorter than the object's confirmed lifespan. Archival data showed the star had maintained its properties for decades, possibly longer. By the end of the first year following detection, more than 20 independent research groups had published observational studies. None offered a definitive explanation. Instead, a shared vocabulary emerged in conferences and journals. The object was described as incompatible, non-convergent, and theoretically unplaceable. Such language reflected not confusion, but the recognition that the data were robust and the problem was fundamental. Subsequent analyses focused on identifying which specific assumptions in stellar structure models were most directly challenged by the observations. Researchers compared the object's measured luminosity, inferred mass, and stability against established limits, such as the Eddington luminosity and standard mass-radius relations. In multiple cases, the observed parameters exceeded model predictions without triggering the expected dynamical responses, highlighting precise areas of discrepancy between theory and measurement. As additional observations were collected, newly acquired datasets remained consistent with earlier measurements and did not reduce the discrepancy between observed properties and theoretical predictions. The object continued to be prioritized in observing schedules and modeling efforts, with studies focusing on stellar formation pathways, internal energy transport, and stability criteria relevant to its measured parameters. How stars are supposed to be born. To understand why the anomalous star immediately triggered alarm, astrophysicists had to revisit the process by which stars are expected to form and why that process imposes strict boundaries. Star formation is not an open-ended phenomenon. It unfolds within tightly constrained physical conditions that limit how massive, luminous, and long-lived a star can be from the very beginning of its existence. The process begins inside molecular clouds, vast regions of cold gas and dust, composed primarily of hydrogen molecules with traces of helium and heavier elements. These clouds can span tens to hundreds of light years, but despite their size, their material is diffuse. Typical densities are only a few hundred particles per cubic centimeter, far emptier than any vacuum created on Earth. For a star to form, a portion of this cloud must undergo gravitational collapse, overcoming internal gas pressure, turbulence, and magnetic fields. Triggers for collapse vary. Shock waves from nearby supernovae, spiral arm density waves, or cloud-cloud collisions can compress regions of gas enough for gravity to take over. Once collapse begins, the cloud fragment heats up as gravitational energy converts into thermal motion. This heating counteracts further collapse, meaning that only fragments above a certain mass can continue contracting. This balance defines the initial mass scale of stars and explains why most stars form with masses similar to or smaller than the Sunday. As collapse proceeds, conservation of angular momentum causes the material to spin faster, flattening into a rotating disk around a dense central core. This protostellar disk plays a critical regulatory role. It feeds material inward while simultaneously launching bipolar outflows that expel excess angular momentum. Observations from the Atacama Large Millimeter submillimeter array have shown these outflows to be nearly universal in forming stars, acting as a braking mechanism that prevents uncontrolled growth. The protostar itself is not yet a true star. Its core temperature is still too low to sustain hydrogen fusion. Instead, it shines due to gravitational contraction. At this stage, the object's mass increases through accretion from the surrounding disk. But this growth is self-limiting. As the protostar gains mass, its luminosity increases, heating nearby gas and driving winds that push material away. This feedback sharply reduces the rate at which additional mass can be accumulated. For low and intermediate mass stars, this balance produces objects ranging from roughly 1/10 to several times the mass of the Sunday. For high-mass stars, the situation becomes even more restrictive. Once a protostar exceeds about 8 solar masses, radiation pressure becomes a dominant force. Photons streaming outward exert pressure on infalling gas, creating a powerful opposing force that can halt accretion entirely. Modern simulations show that even with disk-mediated accretion channels, this process imposes a natural upper limit. Another constraint arises from opacity, which depends on the abundance of heavy elements. In regions with higher metallicity, dust grains absorb radiation efficiently, enhancing radiation pressure and limiting growth. In low metallicity environments, reduced opacity allows slightly higher masses, but only within narrow margins. Observations of massive stars in nearby dwarf galaxies suggest upper limits around 100 to 150 solar masses, even under favourable conditions. Once the core temperature reaches approximately 10 million Kelvin, hydrogen fusion ignites, marking the birth of a main sequence star. At this point, the star enters hydrostatic equilibrium, balancing inward gravitational force with outward pressure from nuclear reactions. This equilibrium is delicate. The rate of fusion depends sensitively on temperature and density, creating a natural thermostat. If fusion accelerates, the core expands and cools, reducing the reaction rate. If fusion slows, gravity compresses the core, increasing temperature and restoring balance. This self-regulating behavior is central to stellar stability, but it also imposes limits. As mass increases, the core must produce disproportionately more energy to counteract stronger gravity. Above certain thresholds, the required energy output generates radiation pressure that destabilizes the outer layers. Stars approaching this regime are observed to shed mass through intense stellar winds, sometimes losing more material than they gain over their lifetimes. Massive star formation is further constrained by timescales. High-mass protostars evolve rapidly, igniting fusion while still embedded in their natal clouds. Their intense radiation disrupts the surrounding environment, halting further accretion. This is why massive stars are rare and short-lived, often burning through their nuclear fuel in only a few million years before ending their lives in supernova explosions. Statistical studies of stellar populations reinforce these limits. Surveys of star-forming regions such as the Orion Nebula, the Carina Nebula, and the Tarantula Nebula show a steep decline in the number of stars above certain masses. This distribution, known as the initial mass function, has been measured across different galaxies and environments. While its exact shape varies slightly, its upper cutoff appears remarkably consistent, suggesting a universal physical mechanism rather than local coincidence. Numerical simulations incorporating gravity, radiation, transport, magnetic fields, and turbulence reproduce this cutoff with striking regularity. When parameters are adjusted to allow higher masses, the simulations either fail to converge or produce stars that rapidly eject mass until they fall back below stability thresholds. No simulation using established physics produces long-lived stars with the extreme properties observed in the anomalous object. Equally important is the role of stellar feedback on the surrounding cloud. Massive stars ionize nearby hydrogen, creating expanding H2 regions that erode the parent cloud. This process not only limits their own growth, but also suppresses the formation of additional massive stars nearby. The result is an environment hostile to runaway mass accumulation, especially over extended periods. Binary and multiple star systems introduce additional complexity, but they do not remove the limits. While mergers can temporarily create more massive objects, such products are predicted to be unstable and short-lived. Observationally, merger remnants exhibit rapid rotation, chemical mixing, and irregular variability, none of which align with the long-term stability observed in the anomalous star. These processes collectively describe the sequence of physical mechanisms active during star formation, including gravitational collapse, angular momentum regulation, radiative feedback, and mass loss. Each mechanism has been independently examined through theoretical models, numerical simulations, and observational surveys across multiple galactic environments, with measured stellar properties consistently falling within defined mass and luminosity ranges. The object described in the previous chapter was evaluated against this framework by comparing its inferred properties to established limits derived from star formation models. Initial analyses focused on discrepancies between predicted and measured values, particularly in parameters related to mass accumulation and radiative stability. Among these parameters, mass estimates showed the largest deviation from theoretical expectations, the mass that breaks the upper limit. Once the framework of star formation was firmly established, attention turned to the single parameter that most forcefully placed the anomalous object outside that framework: its mass. Mass is the defining property of a star. It determines luminosity, lifetime, internal structure, and eventual fate. Because of this, mass estimates are among the most carefully scrutinized measurements in astrophysics, especially for objects that appear to challenge known limits. Determining stellar mass is rarely straightforward. Unlike planets, stars cannot be weighed directly. Instead, astronomers infer mass using indirect methods that depend on gravity's influence on light, motion, and surrounding material. In this case, several independent techniques converged on the same unsettling result. The star's mass estimate exceeded 200 solar masses, with some analyses pushing the value closer to 300. Even the most conservative interpretations placed it well above the generally accepted upper limit for stable stars. The first estimates came from luminosity-based scaling. For most stars, brightness increases steeply with mass. Decades of observation have shown that stars above 50 solar masses already approach extreme regimes of radiation pressure and instability. Known record holders such as R13601, located in the Tarantula Nebula, are estimated at around 150 to 200 solar masses and are considered exceptional outliers. The anomalous star appeared to rival or exceed these values while lacking their violent behavior. Spectroscopic measurements provided further constraints. The widths of certain spectral lines revealed information about surface gravity. When combined with luminosity and temperature data, these measurements narrowed the possible mass range. The inferred gravity was inconsistent with lower mass interpretations. Reducing the mass to acceptable theoretical values would require surface gravities far stronger than those observed, creating a mismatch that could not be reconciled through measurement error alone. Gravitational influence on nearby material offered another avenue. Although the star was relatively isolated, subtle perturbations in surrounding gas clouds were detected through radio observations. These perturbations indicated a gravitational well deeper than expected for stars near the conventional upper mass limit. While not precise enough to yield a single number, the data reinforced the conclusion that the object's mass was extraordinarily high. The concept of an upper mass limit for stars is not arbitrary. It emerges from a balance between gravity and radiation. As mass increases, the energy produced in the core rises dramatically. This energy escapes as radiation, which exerts outward pressure on the star's outer layers. Beyond a certain point, this pressure counteracts gravity so strongly that additional mass cannot be retained. This threshold is not sharp, but decades of modelling place it in the range of 100 to 150 solar masses for most environments. Attempts to push beyond this limit in simulations have consistently failed. When researchers artificially increase accretion rates or reduce opacity to allow higher masses, the simulated stars respond by shedding mass through intense winds or eruptive events. These stars may briefly exceed the limit, but they rapidly return below it. Long-term stability at extreme masses has not emerged in any model using established physics. This is why the anomalous star's inferred mass caused immediate concern. If the estimates were correct, the star was not merely large, it occupied a regime where gravity, radiation, and internal pressure should be fundamentally incompatible. Theoretical work by astrophysicists Stan Woosley and others has shown that stars above certain masses are prone to catastrophic instabilities, including pair instability processes that disrupt the star entirely. Yet no such signatures were observed. The problem deepened when variability studies were considered. Massive stars near the upper limit often show strong photometric and spectroscopic variability as their outer layers respond to internal instabilities. Historical examples include Eta Carinae, which underwent dramatic outbursts and mass loss. The anomalous star, by contrast, displayed only minor fluctuations. Its light curve lacked the irregular spikes or dips expected from a star struggling to maintain equilibrium at extreme mass. Another possibility explored was that the star was a recent merger of multiple massive stars. Such mergers can temporarily create objects with very high mass. However, merger remnants are predicted to rotate rapidly and exhibit chemical signatures of deep mixing. Observations showed neither. The star's rotational velocity, while notable, was not extreme, and its surface composition did not display the abundance anomalies typical of merger products. Binary explanations were also tested rigorously. In many cases, two or more stars can masquerade as a single brighter object if unresolved. High-resolution imaging ruled this out decisively. The point spread function remained singular even at resolutions capable of separating close binaries at the star's distance. Radial velocity measurements showed no periodic shifts indicative of orbital motion. The star was alone. Environmental arguments offered no relief. Even in the most massive star clusters, such as those found in starburst galaxies, the most extreme stars adhere to similar mass limits. Statistical analyses of thousands of clusters across different galaxies show a consistent truncation at the high mass end. The anomalous star did not reside in such a cluster, making its mass even harder to explain. The uncertainty margins themselves became a topic of debate. Could systematic errors inflate the mass estimate? Teams revisited assumptions about opacity, distance, and extinction. Each revision shaved off small amounts, but never enough to bring the star into compliance with theory. Even at the lowest plausible mass consistent with the data, the object remained far beyond accepted stability limits. Stellar evolution models predict that stars with very high mass consume nuclear fuel rapidly and experience short lifespans, often accompanied by strong instability or explosive endpoints. Observational data for this object showed no evidence of rapid evolutionary change, imminent collapse, or large-scale mass loss during the period of monitoring, despite its inferred mass placing it in a regime where such behavior is expected. Ongoing analyses repeatedly returned to mass estimates as a central constraint. Adjustments to other parameters failed to reconcile the object's observed behavior with theoretical models, unless the mass value was altered beyond what observational data permitted. Conversely, retaining the measured mass placed the object outside the range supported by existing stellar physics. This impasse forced researchers to examine whether other fundamental properties might be misleading. If mass alone could not explain the star's behavior, Perhaps its internal conditions differed radically from expectations. That question led directly to the next puzzle revealed by observation: the star's temperature profile, which refused to align with any known model of nuclear fusion-driven energy production. A temperature profile that defies fusion models. With mass estimates already straining the limits of accepted theory, researchers turned to the star's temperature as the next critical diagnostic. Temperature is not merely a surface property. It encodes information about a star's internal energy production, transport mechanisms, and evolutionary state. For decades, stellar temperature profiles have been among the most reliable indicators of how a star generates and distributes energy. In this case, they deepened the mystery rather than clarifying it. Surface temperature is inferred primarily through spectroscopy. By analyzing the relative strengths of absorption and emission lines produced by different elements, astronomers can determine the temperature of a star's photosphere with remarkable precision. Early measurements of the anomalous star placed its surface temperature in a range typical of very massive, luminous stars, but not extreme enough to justify the ionization states observed in its spectrum. The discrepancy immediately raised red flags, prompting multiple teams to undertake independent spectroscopic campaigns. Observatories involved included the Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Subaru Telescope in Japan. Each institution reported consistent results, ruling out instrumental error or calibration problems. In standard stellar models, surface temperature scales with mass and luminosity in predictable ways. Extremely massive stars, particularly those exceeding 100 solar masses, are expected to have surface temperatures exceeding 40,000 Kelvin, sometimes approaching 50,000 Kelvin, in their most luminous phases. These temperatures produce characteristic spectral features dominated by highly ionized helium and metals such as nitrogen, oxygen, and carbon. Yet, the anomalous star exhibited strong signatures of extreme ionization typical of hotter stars, while its inferred surface temperature remained significantly lower. This unusual combination suggested that the star was generating high-energy photons at a rate inconsistent with its photospheric temperature, an unprecedented situation. The inferred temperature gradient beneath the surface was analyzed using spectral data combined with luminosity and radius estimates. Reconstructed internal profiles indicated a core temperature that, according to standard fusion models, would not produce the observed energy output. In conventional models, higher luminosity requires higher core temperatures to drive faster nuclear reactions. But the reconstructed data showed that the expected relationship between core temperature and luminosity did not align with the measurements. To refine measurements, astronomers launched a series of observational campaigns across the electromagnetic spectrum. Ultraviolet spectroscopy from Hubble focused on ionization edges sensitive to small temperature changes, while infrared observations using the James Webb Space Telescope probed deeper atmospheric layers. X-ray data from Chandra provided indirect insights into high-energy processes closer to the core. Radio observations were used to examine the outer stellar envelope and detect possible winds or thermal radio emissions. Each dataset added resolution to the temperature profile, but failed to reconcile the core and surface temperatures with conventional fusion theory. One hypothesis considered whether unusual chemical composition could account for the anomaly. Elemental abundances affect opacity, which in turn influences how energy moves from the core to the surface. If the star were deficient in elements like iron or silicon, radiation could escape more efficiently, allowing high luminosity at lower apparent temperatures. Detailed abundance analyses, using high-resolution spectra from ESO's Very Large Telescope and Keck Observatory, however, showed only moderate anomalies. The star's composition was unusual in subtle ways, slightly lower iron and carbon abundances than expected for a star of its class, but insufficient to explain the extreme energy output. Another possibility examined was energy transport. In most stars, energy moves outward through radiation, convection, or a combination of both. Massive stars are typically dominated by radiative transport, with energy diffusing outward through countless photon-particle interactions. If the anomalous star possessed an unknown or enhanced transport mechanism, it might explain the flattened temperature gradient. Computational models were adjusted to test extreme transport efficiencies, including higher radiative conductivity and partial turbulent convection in regions normally dominated by radiation. Even these extreme scenarios, however, failed to reproduce observations without rendering the star dynamically unstable, indicating that conventional energy transport mechanisms alone could not account for the data. Time-dependent behavior was examined through long-term monitoring over several years, which indicated that the surface temperature remained stable. High-mass stars nearing theoretical limits often display photometric and spectroscopic variability due to expansion and contraction of their outer layers. The anomalous star exhibited only minor, quasi-periodic variations, without the spikes or dips observed in cases such as Eta Carinae and P Cygni. These observations indicate that the star's temperature and luminosity were unusually consistent compared with expectations for similar mass stars. Comparisons with known extreme stars only emphasized the anomaly. Eta Carinae, for instance, undergoes dramatic eruptions and temperature fluctuations linked to episodic mass loss. Wolf-Rayet stars display extremely high surface temperatures, but are stripped of their outer hydrogen layers, a state incompatible with the hydrogen lines present in the anomalous star's spectrum. R13601, one of the most massive stars known, combines extremely high temperature with extreme luminosity, but shows variable wind activity consistent with radiation pressure limits. The anomalous star fit neatly into none of these categories. Theoretical analysis of fusion processes offered little reassurance. Hydrogen fusion through the proton-proton chain, or CNO cycle, requires core temperatures above 10 million Kelvin. If the core temperature were lower than expected, fusion rates would drop sharply, reducing luminosity. To compensate, either core density would need to be higher, or alternative reactions such as hot CNO or triple alpha processes would have to dominate earlier than expected. Density estimates derived from mass and radius, however, did not support these alternatives. The star appeared too diffuse for its luminosity, compounding the discrepancy between theoretical models and observation. Researchers also explored the idea that residual gravitational contraction might be powering the star, similar to the energy source in protostars before fusion begins. However, calculations revealed that contraction alone could not sustain the observed luminosity over decades. A protostar of similar mass would radiate an order of magnitude less energy, and the object's long-term stability and temperature profile contradicted a contraction-dominated phase. Even after exhaustive investigation, including non-local thermodynamic equilibrium modeling and adjustments to opacities, the temperature-luminosity mismatch persisted. Attempts to invoke systematic observational errors were dismissed after cross-comparing results from Hubble, JWST, Keck, VLT, and Subaru. The temperature appeared to be intrinsically inconsistent with conventional fusion expectations, suggesting that either an unknown internal process or an unrecognized energy transport mechanism was at play. The star's radius, inferred from luminosity and temperature, presented additional challenges. Calculations indicated that it was smaller than expected for dissipating energy gradually, yet larger than expected to confine the pressures implied by its mass. No single adjustment in temperature, radius, or composition reconciled all observed parameters, with conflicting constraints arising from different measured properties. Research then emphasized detailed analysis of the star's emitted light. Since internal fusion processes and temperature gradients did not fully account for the energy output, astronomers examined spectral features to infer physical conditions throughout the atmosphere and near the core. Analyses focused on line broadening, ionization ratios, and continuum flux to extract information about internal energy generation and transport that was inconsistent with existing models. The light signature no model predicted. The anomalous star's light carried an enigma more profound than its mass or temperature. Its spectral fingerprint simply did not match anything in the astrophysical record. When astronomers first examined the high-resolution spectra collected by the Hubble Space Telescope, combined with data from the Very Large Telescope and Keck Observatory, they found patterns in emission and absorption lines that no existing stellar model could reproduce. Unlike typical stars, whose spectral lines reflect predictable distributions of elements, ionization states, and atmospheric motions, this star exhibited a combination of features that defied classification. Typically, massive stars display spectra dominated by hydrogen and helium, with trace metals appearing according to their age and metallicity. Ionization states in the outer atmosphere follow well-understood thermodynamic relations. Hotter cores produce higher degrees of ionization, while cooler envelopes maintain neutral or singly ionized elements. In this case, however, astronomers observed simultaneous signatures of extremely high ionization levels, normally requiring surface temperatures above 60,000 Kelvin, coexisting with molecular absorption lines that should only survive at temperatures below 20,000 Kelvin. Such a dichotomy implied an atmospheric structure that standard radiative transfer and convection models could not support. One striking anomaly involved the nitrogen lines. The star displayed NV emission in the ultraviolet, a signature generally observed only in Wolf-Rayet stars approaching the end of their brief lives. Yet its hydrogen lines were strong and unstripped, inconsistent with a Wolf-Rayet classification. At the same time, oxygen lines that typically dominate spectra at similar ionization levels were unexpectedly weak. This combination of strong, high ionization nitrogen and weak oxygen had no precedent, even among the most massive stars in the Large Magellanic Cloud or the Carina Nebula. The carbon lines were equally perplexing. CIV emission, indicative of temperatures in excess of 50,000 Kelvin, appeared alongside molecular CH absorption, usually obliterated at even 30,000 Kelvin. Spectral modelling using both LTE or local thermodynamic equilibrium and non-LTE approaches failed to reproduce the observed ratios. Adjusting temperatures, densities, and metallicities could marginally improve fits for certain lines, but no model simultaneously matched the full spectrum across ultraviolet, optical, and near-infrared wavelengths. Velocity broadening offered another layer of mystery. Spectral lines normally provide information about rotational velocities, stellar winds, and turbulence in the atmosphere. In this star, some high ionization lines were extremely broad, consistent with gas moving at thousands of kilometers per second, while nearby low ionization and molecular lines remained narrow, indicating regions of gas moving at only tens of kilometers per second. This implied an extreme decoupling of atmospheric layers, with high-velocity ionized gas coexisting beside relatively calm molecular regions. Current hydrodynamic models of massive stars do not allow for such coexisting regimes, since momentum and energy transport should homogenize velocities over time. Further anomalies emerged when the team analyzed forbidden lines, which arise in very low-density regions where electrons collide infrequently. The star's spectrum exhibited forbidden transitions from iron and sulfur in regions that, according to luminosity and mass estimates, should have been too dense for such lines to exist. This indicated the presence of pockets of rarefied gas within the star's outer envelope, yet stable against mixing or collapse, a situation not predicted by stellar structure theory. Researchers also examined the continuum emission across the full spectral range. Massive stars radiate approximately as blackbodies, with slight modifications due to atmospheric opacity. The anomalous star, however, displayed a continuum inconsistent with standard models. There was a pronounced ultraviolet excess, suggesting additional energy production at high frequencies, combined with an unexpected infrared plateau, implying cooler regions emitting strongly at longer wavelengths. Attempts to model the spectrum as a composite of multiple unresolved stars failed. No combination of blackbody curves, weighted by plausible stellar masses, reproduced the observed energy distribution. The line ratios offered further surprises. Diagnostic ratios, like He3 4000, 686 to H-beta, often used to estimate effective temperatures and ionizing fluxes, were far higher than any single star model could produce. Meanwhile, ratios of metals such as Psi4 to Psi3 implied a cooler region coexisting directly alongside the hotter zones. Observations suggest that standard energy transport mechanisms, including radiation and convection, cannot account for the simultaneous production of these line ratios. Temporal monitoring of spectral lines added another layer of complexity. Unlike massive stars near the Eddington limit, which often display line profile variations due to pulsations or wind instabilities, this star's lines remained extraordinarily stable over years. High ionization emissions, molecular absorption, and forbidden transitions all showed minor fluctuations of less than 1%, implying that the mechanisms producing these features were remarkably steady despite the extreme energy density implied by the luminosity and mass. Magnetohydrodynamic effects were examined as a potential explanation. Strong magnetic fields can influence line formation, induce anisotropies in emission, and stabilize atmospheric layers against convection. Observations revealed hints of Zeeman splitting in several metal lines, suggesting field strength significantly higher than expected for a non-degenerate massive star. However, magnetic fields of this magnitude should alter rotational profiles, suppress large-scale convection, and potentially inhibit hydrogen fusion. Yet none of these effects matched other observational constraints. The star's light also revealed peculiar Doppler shifts. While most spectral features were stationary relative to the star's center of mass, several high ionization lines exhibited subtle periodic shifts over timescales of weeks, corresponding to velocities of hundreds of kilometers per second. These shifts could not be explained by orbital motion, stellar pulsations, or wind clumping, suggesting an internal dynamic that transported ionized material rapidly while leaving other layers largely unaffected. Even the interaction of the star's radiation with its immediate environment presented unusual results. Surrounding gas clouds were illuminated in ways inconsistent with the star's measured temperature. Ultraviolet emission was sufficient to ionize nearby hydrogen, but did not account for the excitation of observed metal lines in the surrounding nebula. Measurements indicate that the star was producing a photon spectrum with a higher proportion of extreme energy photons than predicted for a star of its mass and temperature. Observations indicated that internal and atmospheric processes occurred in decoupled regimes. High ionization regions coexisted with cold molecular material. Forbidden line-emitting regions persisted in areas of higher density than expected. The spectral continuum exhibited both ultraviolet excesses and infrared plateaus simultaneously, and temporal monitoring showed line stability over years. Modeling with known stellar physics fusion, radiative transfer, convection, rotation, and magnetic fields did not reproduce the full observed spectrum. Simulations treating the star as a composite of multiple unresolved objects, a binary, or a recent merger, achieved partial matches for select line strengths and ionization states. But no configuration reproduced the complete spectrum across ultraviolet, optical, and infrared wavelengths. The star's spectral fingerprint revealed line strengths, ionization states, and continuum features not reproduced by current stellar models. Observations indicated simultaneous presence of high-energy emissions and cooler molecular absorption, a combination not predicted by models relying on fusion-driven energy transport, convection, or radiation. Spectral data suggest that multiple atmospheric and internal regions were operating under conditions not captured in standard theoretical frameworks. Rotation rates beyond structural stability. Following the revelations encoded in the star's spectrum, astrophysicists turned their attention to its rotation, a property that should have revealed the object's internal dynamics and further confirmed the impossible conditions suggested by its mass, temperature, and light. High-mass stars are already challenging to model in terms of angular momentum, but the anomalous star exhibited rotation rates that were extreme even by the standards of the fastest known stellar rotators. What astronomers discovered pushed the boundaries of conventional structural stability. Rotation in stars is typically measured through spectral line broadening, specifically by examining Doppler shifts in absorption lines. The faster a star spins, the wider these lines appear. Observations from Keck Observatory and the European Southern Observatory indicated rotational velocities approaching 450 kilometers per second at the equator. By comparison, Achernar, one of the fastest known stars in the Milky Way, spins at roughly 300 kilometers per second. Despite this high velocity, interferometric and spectroscopic measurements indicated no significant equatorial bulging or mass shedding. Rotation in stars is typically measured through spectral line broadening, specifically by examining Doppler shifts in absorption lines. The faster a star spins, the wider these lines appear. Observations from Keck Observatory and the European Southern Observatory indicated rotational velocities approaching 450 kilometers per second at the equator. By comparison, Achernar, one of the fastest known stars in the Milky Way, spins at roughly 300 kilometers per second. Despite this high velocity, interferometric and spectroscopic measurements indicated no significant equatorial bulging or mass shedding. The distribution of angular momentum inside the star presented another anomaly. In most massive stars, rotation is differential. The core spins faster than the envelope due to conservation of angular momentum during contraction and fusion. In this star, the spectral line profiles, combined with polarimetric observations, suggested a surprisingly uniform rotation across both core and envelope. Models by astrophysicists like Norbert Langer and André Mader indicate that such uniform rotation is nearly impossible without extremely strong internal coupling mechanisms. Magnetic fields can transfer angular momentum from core to envelope, but measurements indicated that while the star possessed a field stronger than most main sequence stars, it was orders of magnitude below what would be required to enforce complete rotational uniformity in an object of this mass. Observations spanning more than a decade, including photometric monitoring from the Transiting Exoplanet Survey satellite and spectroscopic campaigns using Gemini Observatory, revealed negligible change in the rotational profile. High-mass stars with comparable spin rates typically slow down within a few million years due to magnetic braking and mass loss. The star's rotation remained stable, indicating limited deceleration over the observational period. The rotational rate influenced surface temperature distribution through the von Zeipel effect, which predicts hotter poles and cooler equators due to differences in effective gravity. Observational data, particularly interferometric measurements in the near-infrared, confirmed polar brightening at a lower contrast than predicted for a star spinning at 450 km per second. These measurements suggest that surface temperature variation was less pronounced than standard models of radiative and convective transport would predict. Centrifugal instability presents a theoretical challenge. Stars with extreme rotation are prone to structural instabilities, such as bar mode deformation, where the star elongates due to the imbalance between gravity and centrifugal force. Laboratory and simulation studies show that stars reaching more than 70–80% of their critical rotational velocity exhibit rapid deformations and often undergo significant mass ejection. High-resolution adaptive optics imaging of the star indicated a near-spherical shape. Gravity estimates derived from surrounding gas dynamics and spectral lines suggest that the star's structure resisted centrifugal deformation under the observed rotational velocity. Rotation interacts with magnetic fields through magnetorotational coupling, which can influence internal mixing and fusion rates. In fast-rotating massive stars, this coupling often leads to enhanced chemical mixing, bringing helium and heavier elements from the core to the surface. Observations of the anomalous star's surface composition revealed only moderate enrichment, lower than predicted by standard rotational mixing models for an object of this size and spin rate. The combination of rapid rotation and mass affects radiative winds. At high luminosities, the outward pressure from photons interacts with the stellar atmosphere, driving strong mass loss. Rapid rotation further amplifies these winds, particularly along the equator, where centrifugal force reduces effective gravity. Spectroscopic analysis showed a mass loss rate roughly an order of magnitude below theoretical predictions for a star of 200–300 solar masses spinning near breakup speed, indicating that the observed mass retention exceeded standard model expectations. Astrophysicists also examined pulsational behavior linked to rotation. In stars with extreme angular momentum, centrifugal distortion can couple with acoustic modes to produce non-radial pulsations. Such pulsations manifest as periodic variations in brightness and spectral line shifts. Continuous monitoring using Hubble's photometric instruments and the TESS satellite revealed pulsations with amplitudes of less than 0.1%. Standard models for stars of this mass and rotation predict amplitudes of several percent, indicating a measurable discrepancy between observation and model predictions. Rotational velocity also has implications for magnetic field generation. Stars spinning this rapidly often exhibit strong dynamo activity, producing complex and variable magnetic fields. The anomalous star's measured field, while high for a non-degenerate object, was uniform and stable over years of observation. Zeeman spectropolarimetry detected a field strength of roughly 20,000 Gauss, much stronger than typical O-type stars, which range from a few hundred to a few thousand Gauss. Observed rotational stability was maintained under this magnetic field, though its full interaction with rotation remains a subject of quantitative study. Comparisons to the fastest known rotators provide data context. VFTS 102 inches, the Large Magellanic Cloud, spins at around 600 km per second and exhibits extreme equatorial distortion and mass loss. Achernar spins near 300 km per second, producing significant polar brightening and circumstellar emission. Observations of the anomalous star show it maintained near spherical shape, exhibited limited mass loss, and had a relatively uniform surface temperature despite similar or higher rotation speeds. Researchers also considered whether past events could explain the rotation. Mergers of massive stars can produce rapid spin, but such remnants are expected to show chemical anomalies, extreme rotation gradients, and mass loss signatures. The anomalous star showed none of these merger indicators. Binary interaction explanations were also ruled out. Radial velocity monitoring over a decade revealed no companions or orbital modulation. Observational data indicate that the star's rotation is consistent with an intrinsic property rather than the result of recent external events. Centrifugal forces, magnetic fields, radiative winds, and internal dynamics were expected to produce structural changes or mass loss at the observed rotation rate. Observations show the star remained nearly spherical, steadily spinning, with angular momentum preserved over the decade-long monitoring period. The observed combination of rotation, mass, and surface characteristics does not match existing model predictions for stars of similar parameters. The star's rotational behavior, combined with its mass, temperature, and spectral features, prompted further investigation into its gravitational properties. Subsequent studies aim to measure the star's surface gravity and compare it with mass estimates derived from luminosity and spectral analysis. Observational campaigns were designed to reconcile rotational velocity and gravity with theoretical models of stellar structure, gravity measurements that don't match the mass. After unraveling the extreme rotational behavior of the anomalous star, astronomers turned to a force that governs every star, yet revealed new contradictions in this case: gravity. Gravity should provide the fundamental check on mass, dictating how stellar material is confined, how energy is transported, and how rotation is balanced. For the anomalous star, however, multiple measurements suggested that gravitational behavior was inconsistent with its already extraordinary mass. The first hint came from orbital perturbations of nearby stars. Located within a dense cluster roughly 25,000 light-years from Earth, the star is surrounded by dozens of companion stars whose orbits can be tracked precisely over decades. Using data from the Hubble Space Telescope, the European Southern Observatory, and Gaia, astronomers attempted to determine the gravitational influence exerted by the star. Standard Newtonian mechanics predicts that a 250-300 solar mass object should cause measurable accelerations in nearby stars, yet observed deviations were significantly smaller than expected. Stars orbiting at distances of 0.1 to 0.5 light-years showed perturbations consistent with a gravitational mass closer to 150 solar masses. Observations indicated a difference between the star's luminous mass and the gravitational mass inferred from nearby stellar motions. One explanation considered was that the star might contain a large fraction of dark, non-luminous matter or exotic particles, but detailed spectral and asteroseismic data contradicted this. There was no evidence of unusual density concentrations or hidden cores that could reconcile gravitational and luminous mass estimates. Surface gravity measurements provided another dimension of the problem. Spectroscopic analysis of pressure-sensitive lines in the star's atmosphere, particularly ionized helium and metal triplets, allows astronomers to estimate the surface gravity in terms of g-force. For a star of this size, surface gravity should reach tens of meters per second squared in the equatorial regions and hundreds in the polar zones, if rotation is considered. Observations indicated values only half as large as predictions based on the star's mass and radius. Even accounting for rotational flattening and centrifugal reduction at the equator, the measured surface gravity could not be reconciled with the mass required to produce the observed luminosity and temperature. Gravitational lensing offered yet another method for verification. The star lies behind a patch of diffuse interstellar dust and a dense background of fainter stars, providing opportunities to detect subtle bending of light as it passes nearby. Observations from the Hubble Space Telescope and the Very Large Telescope's adaptive optics systems showed lensing effects weaker than expected. Given the star's estimated 300 solar masses, gravitational lensing should have produced detectable microlensing events in background stars on timescales of days to weeks. In practice, monitoring over 5 years revealed only marginal lensing signatures, again implying a gravitational influence smaller than expected. The discrepancy extended to orbital dynamics of circumstellar material. Radio interferometry using ALMA revealed ionized gas moving around the star at speeds inconsistent with both the mass inferred from luminosity and the extreme rotational velocities. Gas in equatorial regions displayed orbital motion, suggesting a central gravitational mass roughly 40–50% lower than the stellar mass derived from energy output. Attempts to model this with a combination of stellar winds and radiation pressure failed. The observed velocity gradients required a central mass that simply could not exist according to standard stellar structure equations. Tidal effects provided further evidence. Neighboring massive stars in the cluster exhibited periodic distortions and oscillations due to tidal interactions. Observed tidal features were weaker than expected based on the star's luminosity-derived mass. Cluster dynamics measurements indicated a gravitational influence lower than predicted by standard mass estimates. Another observation came from asteroseismology. Stellar oscillations produce characteristic frequencies that depend directly on the density and gravity inside the star. Using continuous monitoring from TESS and follow-up spectroscopy, researchers extracted oscillation modes. The modes were detectable, but at amplitudes and frequencies inconsistent with a homogeneous, high-mass star. Specifically, some radial modes suggested a lower average internal gravity, while non-radial modes indicated internal stratification more extreme than predicted by standard models. Theoretical models considered extreme rotation and internal magnetic fields. A strong poloidal magnetic field could redistribute mass, reducing effective gravity at the surface, while extreme rotation flattens the star and lowers equatorial gravity. Simulations by research groups, led by Stan Woosley and Norbert Langer, combined these effects in massive stars up to 300 solar masses. The simulations predicted surface gravity, rotation, and mass values that differed from those measured for the anomalous star. Gravitational anomalies were also noted in the star's high-energy emissions. X-ray observations from Chandra and New Star indicated localized flares and plasma motion that should have been tightly confined by gravity. High-energy gas was observed moving along magnetic loops and traveling large distances with minimal deceleration, implying a gravitational potential lower than predicted by the star's mass. The star's angular momentum affected gravitational measurements. Centrifugal force reduces effective gravity at the equator, but the reduction inferred from rotational measurements and polar flattening accounted for only part of the observed discrepancy. The combined data from rotation and surface gravity measurements indicated a difference of approximately 30–50% between measured and expected gravitational force. Binary scenarios were evaluated. Radial velocity studies over more than a decade revealed no Doppler shifts consistent with orbital motion. Interferometry also failed to resolve multiple components, ruling out close binaries. Hierarchical triple systems did not match the combination of observed luminosity, spectral anomalies, rotation, and measured gravity. Alternative explanations involving dark matter were briefly entertained. Hypothetical particles embedded within the star could alter the gravitational profile without emitting light, but no known particle could survive the extreme temperatures and pressures in such a massive star's interior. Nuclear reactions at the inferred core temperature would destroy or dilute any exotic matter in seconds, making this scenario implausible. The mismatch between mass and gravity extended to the star's immediate neighborhood. Molecular clouds in the cluster, when modeled under the star's gravitational potential, showed motion inconsistent with expectations. Gas clouds within 1 light-year of the star moved as if influenced by a lower mass object. Dense clumps of hydrogen and helium did not accelerate to the velocities predicted by the star's luminosity-derived mass. Observations included orbital perturbations, surface gravity, circumstellar motion, asteroseismic data, tidal interactions, gravitational lensing, and high-energy emissions. Measurements from these methods consistently indicated a gravitational influence lower than that predicted by standard stellar models, even when accounting for rotation, magnetic fields, or multiplicity. For a star with an estimated 200–300 solar masses, the measured gravitational effects on surrounding stars, gas clouds, and high-energy plasma were lower than predicted. Observations indicated that standard models of gravity did not fully account for these measurements. The star exhibited extreme rotation, unusual spectral features, and temperature gradients. Future investigations planned to focus on age and evolution to determine how these properties persisted over observable timescales. The age problem no timeline can solve. After discovering that the anomalous star's gravity failed to match its mass, astronomers confronted another conundrum that further destabilized conventional stellar theory: its age. Stars usually adhere to predictable lifespans based on their mass, luminosity, and fusion processes. High-mass stars burn through hydrogen at extraordinary rates, evolving quickly into supergiants or collapsing into black holes within a few million years. Yet this star defied these expectations, displaying characteristics that made it simultaneously appear extremely young and unusually evolved, a paradox no existing timeline could resolve. One method of estimating stellar age relies on nucleosynthetic byproducts. As stars fuse hydrogen into helium and then heavier elements, isotopic ratios change in predictable ways. Using spectroscopic observations from the Hubble Space Telescope, the Very Large Telescope, and Keck Observatory, researchers measured ratios of carbon to nitrogen, oxygen, isotopes, and trace elements such as magnesium-2,6. The surface composition contained high hydrogen content, while certain isotopic ratios indicated significant nuclear processing consistent with several million years of evolution. The surrounding stellar population offered additional clues. The star resides in a dense cluster with hundreds of stars, whose ages can be determined using isochrone fitting, comparing observed luminosities and temperatures to stellar evolution models. The majority of stars in the cluster were estimated to be 5 to 8 million years old. The anomalous star exhibited spectral features, including helium enrichment in certain layers and enhanced nitrogen, which are typically observed in stars that have evolved through the Wolf-Rayet phase. The star also retained high hydrogen content in the core, indicating it had not yet exhausted hydrogen despite evidence of processed outer layers. Another approach involves the analysis of circumstellar material. Massive stars in early stages often retain protoplanetary disks or envelopes of gas and dust, while evolved stars show signs of wind-blown cavities or enriched nebulae. Infrared observations using Spitzer and ALMA revealed an almost complete lack of circumstellar material around this star. For a star of this mass, the absence of surrounding material is consistent with clearing its neighborhood, while its extreme luminosity and rotational velocity indicate it had not yet entered stages of significant mass loss. Asteroseismology, the study of stellar oscillations, added another dimension to age analysis. In massive stars, pulsation frequencies evolve with the changing internal density profile as the star ages. Continuous monitoring from TESS and Hubble revealed oscillation modes that were both unusually low and unusually high in frequency compared to theoretical predictions. Low-frequency modes indicated a dense, evolved core, while high-frequency modes suggested a less compact envelope, resembling protostellar conditions. The chemical profile provided further observational detail. High-resolution spectroscopy revealed enhanced nitrogen and helium, as well as unexpectedly high lithium and beryllium abundances in the outer layers. Lithium is easily destroyed in stellar interiors and generally vanishes within a few million years in massive stars. While outer layers contained lithium, deeper layers showed signs of advanced nuclear processing, indicating simultaneous presence of unprocessed and processed material. Cluster dynamics provided additional observational context. Stars of comparable mass are often ejected from clusters or experience interactions that affect their evolution. This star occupied the cluster's center, moving in a stable orbit. Spectroscopic analysis showed no signs of chemical homogenization or binary remnants that would indicate a recent merger. Rotation influenced the star's internal mixing and potential lifetime. Rapid rotation can enhance mixing and delay hydrogen depletion. The star exhibited extreme rotational velocity, while stellar rotation models from researchers such as Georges Maynet and Sylvia Ekstrom indicate that such rotation affects the distribution of processed material in cores and envelopes. Nearby, nebular analysis provided additional observational constraints. Massive stars emit ultraviolet radiation, ionizing surrounding hydrogen clouds and producing two regions. Measurements of the ionized gas surrounding this star indicated expansion rates and ionization levels consistent with a star older than 5 million years. Surface and internal spectral analysis showed hydrogen-rich outer layers, which are typically associated with stars around 1 to 2 million years old. Massive stars form in dense molecular clouds, requiring large reservoirs of gas and dust. ALMA observations of the natal cloud showed low metallicity and insufficient mass to produce a star exceeding 200 solar masses according to standard accretion rates. The star exhibits a hydrogen-rich surface, while deeper layers show advanced nuclear processing, indicating simultaneous presence of unprocessed and processed material. Researchers examined isotopic ratios of neon and magnesium in the star's atmosphere. Neon 2,2 enrichment, typically produced after helium burning, was detectable alongside magnesium 2,5 and magnesium 2,6 ratios, indicating partial carbon burning. Both types of nucleosynthetic byproducts were present in observable layers. Attempts were made to place the star within standard evolutionary tracks using Geneva and Mesa models. These simulations could not produce a star with this combination of luminosity, rotation, chemical stratification, and cluster age alignment without affecting energy balance or structure. Some tracks suggested an age younger than 2 million years based on hydrogen content, while others, constrained by processed isotopes, implied ages over 7 million years. A star of this mass is expected to approach core collapse within a few million years, producing either a pair instability supernova or direct collapse into a black hole. Observations revealed no pulsational instabilities, strong mass ejections, or photometric irregularities associated with imminent collapse. High metallicity stars of similar mass in nearby galaxies evolve rapidly due to increased opacity and energy transport efficiency. This star, in a cluster with roughly solar metallicity, exhibited hydrogen-rich outer layers and spectral features indicative of quasi-main sequence conditions, while deeper layers showed evidence of nuclear processing. Star clusters in the Milky Way rarely produce stars exceeding 200 solar masses, and clusters with such stars tend to dissipate gas and dust within a few million years. This star exhibited high mass, rapid rotation, and both chemically young and processed layers while residing in a cluster environment. Observations of the star indicate hydrogen-rich outer layers and rapid rotation, alongside evidence of nuclear processing in deeper layers and chemical stratification. These measurements include processed isotopes, cluster age context, and rotational data that show conflicting indicators of evolutionary stage. Why radiation pressure should have destroyed it? Following the revelations about the star's anomalous age, astrophysicists turned their attention to another fundamental force acting within and upon the star: radiation pressure. In massive stars, radiation pressure is a key determinant of stability. It arises from photons exerting outward force on stellar matter, opposing gravitational confinement. For ordinary stars, radiation pressure increases with luminosity, eventually limiting how massive a star can be before its outer layers are blown away. The anomalous star, however, appeared to exist comfortably above that threshold, defying predictions that it should have torn itself apart long ago. Radiation pressure becomes dominant in stars exceeding roughly 100 solar masses. Observations suggested that this star's luminosity was in excess of 10 million times that of the Sun, placing it well above the theoretical Eddington limit for a star of its mass. The Eddington limit defines the luminosity at which the outward force of radiation equals the inward pull of gravity. Above this limit, the outer layers of a star are expected to become unstable, generating powerful stellar winds that can remove significant mass in short periods. By comparison, the most luminous stars known, such as Eta Carinae, display extreme variability and episodic mass ejections as they approach this limit. Measurements of the star's stellar wind offered insight. Using ultraviolet spectroscopy from the Hubble Space Telescope and X-ray observations from Chandra, astronomers quantified the velocity and density of outflowing gas. Winds were present, but the mass loss rate was only 10 -5 solar masses per year, roughly 10 times lower than predicted for a star of this luminosity and rotation. Observations indicated sustained mass retention over extended timescales. Radiation pressure acts differently in the core and envelope. In the core, photons generated by nuclear fusion must push outward to transport energy. In the envelope, radiation interacts with ions and electrons, exerting outward pressure on the outer layers. For the anomalous star, models of photon transport predicted extreme turbulence, convection, and mass ejection, yet observations indicated a remarkably quiescent envelope. Spectral line widths, normally broadened by turbulent motion in such high radiation environments, were narrower than expected. This suggested that the star's outer layers were somehow stabilized against the forces that should have caused violent pulsations or episodic shedding. The role of opacity was critical. In stellar physics, opacity determines how effectively photons transfer momentum to matter. High metallicity stars have greater opacity, making them more susceptible to radiation-driven instability. The anomalous star displayed a metallicity of roughly 0.8 times solar, measured via absorption lines of iron, silicon, and carbon. Adaptive optics and interferometric imaging revealed no extended envelope or shell ejections. Polarimetric studies revealed further anomalies. Rapid rotation can channel radiation along the poles, producing anisotropic outflows. Observations of polarization in optical and near-infrared wavelengths indicated slight enhancement along the rotational axis, but nowhere near the degree required to account for the star's survival. The photon flux should have driven strong polar winds, yet measured velocities in polar regions were only a few hundred kilometers per second, far below predicted values exceeding 2,000 kilometers per second for comparable luminosity. The star's interior structure also contradicted expectations. Radiation-dominated stars are theoretically prone to envelope inflation, in which the outer layers swell dramatically to accommodate the outward photon pressure. This inflation typically reduces surface gravity, enhances pulsations, and triggers mass loss. Yet radius measurements using interferometry and Gaia parallax data indicated a relatively compact stellar envelope. Its radius, roughly 45 times that of the Sun, was smaller than predicted for a radiation pressure-dominated object with this luminosity, further emphasizing the structural stability puzzle. Instabilities known as photon bubbles were expected in such stars. These arise when radiation pressure locally exceeds gas pressure, creating buoyant pockets that rise rapidly and potentially trigger violent eruptions. X-ray monitoring over 10 years, however, revealed only minor flux fluctuations at the percent level, consistent with ordinary convection but inconsistent with large-scale photon bubble activity. The star maintained stability despite conditions that should have amplified such instabilities. Historical comparison added perspective. Stars like P Cygni and Eta Carinae, with comparable or slightly lower mass and luminosity, undergo periodic outbursts where they shed several solar masses in short timescales. Eta Carinae's great eruption in the 19th century expelled 10 to 20 solar masses over 2 decades. By contrast, the anomalous star, exceeding both mass and luminosity of these stars, exhibited no comparable eruptive history, as confirmed by archival surveys of variable stars and infrared surveys of circumstellar dust. The interaction between radiation pressure and rapid rotation compounded the mystery. Normally, rapid spin enhances equatorial mass loss due to reduced effective gravity, while high radiation accelerates wind along poles. In combination, these effects should produce bipolar nebulae and extreme flattening. Yet, adaptive optics imaging in multiple bands revealed a nearly spherical star lacking the expected bipolar structures or extended shells. Even small-scale structures observed in ultraviolet indicated only modest perturbations, suggesting a damping mechanism countering both centrifugal and radiative forces. Magnetic fields provided a possible, though partial, explanation. Measurements indicated a surface magnetic field of roughly 20,000 Gauss, stronger than typical O-type stars. Magnetic pressure could confine ionized plasma and redistribute photon momentum, reducing mass loss. However, simulations by groups led by Hughes, Mathis, and Stanowocki indicated that such field strengths are insufficient to fully stabilize a star with this mass and luminosity against radiation-driven winds. The anomaly remained unresolved. The radiation problem intersected with age-related measurements. Observed hydrogen content suggested the star had retained a substantial fraction of its fuel, while luminosity measurements indicated sustained high-energy output. Radiation pressure models predict accelerated mass loss under these conditions. Further investigation of high-energy emissions revealed strong ultraviolet and soft X-ray fluxes consistent with intense photon output. Yet spectral modeling showed that, despite these emissions, energy transfer to outer layers did not produce the expected instabilities. This suggested a previously unknown mechanism for energy dissipation, or a structural configuration that allowed radiation to escape without destabilizing the envelope. For stars exceeding 150 solar masses, Eddington ratios above 0.7 are associated with extreme instability. This star's ratio was calculated at 1.2, indicating a photon flux exceeding the stabilizing capacity of gravity. Observations showed only minor luminosity variations. Gas in the immediate vicinity, mapped using ALMA and VLT spectroscopy, showed motions largely dominated by stellar winds rather than radiation-driven ejection. Photon pressure effects on surrounding material appeared limited in scope. The star occupies a regime in which radiation pressure is expected to dominate stellar structure and mass loss. Observations showed limited mass loss, a compact envelope, and minor variability, alongside extreme rotation, anomalous gravity measurements, and conflicting age indicators. Magnetic fields stronger than neutron stars expect. With radiation pressure failing to dismantle the star and gravity behaving in unexpected ways, astrophysicists increasingly focused on magnetism as a potential stabilizing force. Magnetic fields play a critical role in stellar behavior, influencing rotation, mass loss, internal mixing, and energy transport. In ordinary massive stars, magnetic fields are present, but relatively weak, typically ranging from a few hundred to a few thousand Gauss. What observers detected in this star, however, was something entirely different: field strengths, so intense and structured that they bordered on what theory reserves for collapsed objects rather than active, fusion-powered stars. The first indications came from spectropolarimetric observations. Instruments such as ESPADONs at the Canada-France-Hawaii Telescope and HARPSPOL at the ESO La Silla Observatory were used to measure subtle polarization signatures in spectral lines caused by magnetic splitting. These measurements revealed a surface magnetic field consistently measured between 15,000 and 25,000 Gauss across multiple epochs. For comparison, the strongest magnetic fields measured in normal O-type stars rarely exceed 3,000 Gauss. Even highly magnetized massive stars, like NGC 1000, 624-2, previously considered extreme, peak around 20,000 Gauss, but that star is far less massive and luminous than the object under study. The strength alone was not the only notable aspect. The field topology appeared ordered and stable. Magnetic fields in massive stars are often complex, multipolar, and variable, shaped by turbulent convection and rotational shear. In this case, the field geometry was dominated by a large-scale dipolar component, aligned closely with the rotational axis. Over more than 10 years of monitoring, the field strength and orientation showed minimal variation. This configuration is consistent with what is described as a fossil magnetic field, one inherited from the star's formation rather than generated by an active dynamo. Magnetic pressure scales with field strength and can rival or exceed gas pressure in localized regions. In this star, modeling showed that magnetic pressure in parts of the envelope was comparable to, and in some regions exceeded, radiation pressure. Magnetohydrodynamic simulations predict that such conditions are associated with reconnection events, flares, and episodic mass loss. Observational monitoring did not detect such phenomena. High-energy observations added further intrigue. X-ray emissions detected by Chandra revealed a spectrum dominated by hard X-rays, with plasma temperatures exceeding 50 million Kelvin in localized regions. These temperatures are typically associated with magnetic reconnection events, similar to solar flares, but vastly more energetic. Yet the X-ray output was steady rather than flaring, implying a continuous, controlled release of magnetic energy. This behavior resembled neither solar-like dynamos nor the chaotic magnetospheres of young stellar objects. The magnetic field also appeared to exert strong control over the star's wind. Massive stars normally exhibit line-driven winds shaped primarily by radiation pressure. In this star, wind diagnostics showed confinement along magnetic field lines, forming extended magnetospheric structures. Radio observations from the Very Large Array detected non-thermal emission consistent with synchrotron radiation, indicating relativistic electrons trapped within magnetic loops spanning several stellar radii. These magnetospheres were far larger and more stable than those seen around other massive stars, suggesting an unprecedented degree of magnetic dominance over stellar outflows. Magnetic fields can suppress convection and alter energy transport. Suppressing convection in a star of this mass is expected to affect core temperature and internal structure. Asteroseismic data indicated relatively stable internal stratification despite these conditions. Comparisons to neutron stars were made in the literature. Neutron stars, particularly magnetars, are known for magnetic fields exceeding 10-14 Gauss. While the star's field was far weaker in absolute terms, it represented an unusually strong field for a non-degenerate hydrogen-burning star. Scaling arguments have been used to compare magnetic flux across different stellar densities and sizes. Attempts to attribute the field to a dynamo mechanism faced significant obstacles. Dynamos require convective motion and differential rotation to amplify magnetic fields. In massive stars, convection is limited primarily to the core, while the envelope remains largely radiative. Simulations by researchers such as Juri Toomre and Axel Brandenburg showed that even under extreme conditions, dynamos in such stars cannot generate surface fields exceeding a few thousand Gauss. The observed field strength exceeded these predictions by an order of magnitude. The fossil field hypothesis was also strained. Fossil fields are thought to originate from the molecular cloud from which a star forms, compressed and preserved during collapse. However, the natal environment of this star, as examined in previous chapters, lacked the density and coherence to produce such an intense, ordered field. Moreover, maintaining that field through phases of rapid rotation, extreme radiation pressure, and internal mixing should have led to significant decay or reconfiguration, none of which was observed. Magnetic braking was another expected consequence. Strong magnetic fields interacting with stellar winds should efficiently remove angular momentum, slowing rotation over time. This star, despite its immense magnetic field, retained extreme rotational velocity with no measurable spin down. This contradiction suggested that either the magnetic field was decoupled from angular momentum loss mechanisms, or that the wind itself was behaving in an unconventional manner, possibly channeled and recycled back onto the star rather than escaping. The magnetic influence extended into the surrounding environment. Polarized emission from nearby gas clouds indicated alignment with the star's magnetic axis over distances of several light years. The observations showed that the magnetic field extended well beyond the stellar surface. Numerical simulations struggled to cope with these observations. Magnetohydrodynamic models, incorporating realistic rotation, radiation pressure, and field strength, either failed to converge or produced stars that rapidly destabilized. Some simulations resulted in magnetic buoyancy tearing the envelope apart. Others led to catastrophic reconnection events that would have produced observable flares and mass ejections. None matched the calm persistence seen in reality. The presence of a strong magnetic field intersected with other observed properties, including mass loss rates, radiation pressure behavior, and rotational uniformity. Modeling indicated that magnetic effects influence stability, energy dissipation, and angular momentum evolution. Independent teams using different instruments, wavelengths, and analysis techniques reported similar magnetic field strengths and configurations. The consistency of measurements across methods supported the presence of a strong, ordered magnetic field. The star was classified as an actively luminous object exhibiting strong, stable magnetic fields. Its magnetic properties required explanation within the context of gravity, radiation, and rotation. As magnetic field measurements were incorporated into analysis, researchers expanded observations to the surrounding environment to examine potential formation and interaction signatures, the environment that should not allow it. As magnetism failed to fully explain how the star maintained its integrity, astrophysicists widened their focus beyond the star itself to the region in which it exists. Stellar environments are not passive backdrops. They strongly influence how stars form, grow, and evolve. For the anomalous star, its surroundings introduced yet another contradiction. Every measurable aspect of its galactic neighborhood indicated that such an object should never have formed there in the first place. The star is embedded in a young stellar cluster located in the inner region of the Milky Way, approximately 25,000 light-years from Earth. This cluster, catalogued through surveys conducted by Gaia and the Vista variables in the Via Lactea project, contains several hundred stars with masses ranging from a fraction of the Sun to about 60 solar masses. While the cluster is dense by galactic standards, its total mass is estimated at roughly 50,000 solar masses, far below what is typically required to form stars, exceeding 200 solar masses through conventional accretion processes. Star formation theory predicts that the most massive stars form in the densest, most turbulent molecular clouds, where gas inflow rates can exceed 10⁻³ solar masses per year. Observations of the natal cloud associated with this cluster, using ALMA and the Atacama Pathfinder experiment, revealed peak gas densities and inflow rates insufficient to support the formation of such an extreme object. The cloud's total mass was estimated at under 200,000 solar masses before star formation began, with fragmentation already underway. Under these conditions, competitive accretion models predict an upper stellar mass limit closer to 8,100 solar masses. Metallicity posed another serious problem. Spectroscopic analysis of nearby stars and gas showed a metallicity slightly below solar, approximately 0, 8 times the Sun's heavy element abundance. While this is not exceptionally low, it is still high enough to enhance opacity in collapsing gas clouds. Higher opacity increases radiation pressure during star formation, which limits how much mass a protostar can accumulate before accretion is halted. In environments with similar metallicity, observed stellar masses rarely exceed 120 solar masses. The anomalous star's inferred mass far exceeded this empirical ceiling. Radiation feedback from neighboring stars further complicated the picture. The cluster hosts several O-type stars whose intense ultraviolet radiation ionizes surrounding gas, heating it and driving it away from dense regions. Simulations by researchers such as Matthew Bate and Mark Krumholtz show that in such environments, radiation feedback strongly suppresses the growth of very massive protostars. Yet, despite this hostile radiative environment, the anomalous star appears to have grown uninterrupted, without evidence of truncated accretion or early mass loss. The spatial distribution of stars in the cluster added to the mystery. The anomalous star sits near the cluster's center, but dynamical modeling indicates that it did not migrate there through mass segregation. Its velocity relative to the cluster average is low, suggesting it formed close to its present location. This contradicts scenarios where massive stars form elsewhere and sink toward the center over time. If it formed in situ, then the local conditions must have supported its growth conditions that no longer appear to exist. Gas kinematics offered additional constraints. Molecular line observations showed that the velocity dispersion in the natal cloud was modest, around 2-3 km per second. Such low turbulence is insufficient to prevent fragmentation into many smaller cores, a process that normally limits the formation of extremely massive stars. High-mass star formation models require turbulent support to funnel gas into a single growing object. The absence of such turbulence makes the star's existence even harder to explain. The lack of a surrounding massive cluster was equally problematic. Observationally, the most massive stars tend to form in the most massive clusters. R136 in the Large Magellanic Cloud, home to stars approaching 150 solar masses, resides in a cluster exceeding 100,000 solar masses. By contrast, the cluster hosting the anomalous star is smaller and less extreme. Statistical models of cluster mass functions indicate that forming a star above 200 solar masses in such an environment has a probability of less than 1 in 10 million. The interstellar radiation field in the region also works against massive star formation. Measurements from infrared surveys showed elevated background radiation from nearby star-forming regions and supernova remnants. This radiation heats molecular clouds, increasing thermal pressure and further inhibiting collapse. Despite this, the anomalous star not only formed, but did so without leaving behind an unusually massive or disturbed remnant cloud, as would be expected if it had accreted such an enormous amount of material. Chemical homogeneity within the cluster posed another issue. If the star had formed through mergers of multiple protostars, a mechanism sometimes invoked to explain extreme masses, there should be signs of chemical diversity or anomalies in the surrounding stellar population. Detailed abundant studies of neighbouring stars revealed no such signatures. Their compositions were remarkably uniform, inconsistent with a history of violent mergers or repeated accretion events involving chemically distinct progenitors. The absence of supernova remnants was also telling. Massive star formation often triggers early supernovae that reshape the environment. No such remnants were detected near the cluster, indicating a relatively calm formation history. This further undermined scenarios involving rapid, chaotic processes capable of assembling a star of this scale. Even external influences failed to provide an explanation. Galactic tidal forces, spiral arm compression, and cloud-cloud collisions can occasionally create conditions favourable for massive star formation. However, orbital reconstruction of the cluster's motion through the galaxy showed no recent passage through a spiral arm or evidence of a high-velocity cloud collision. The cluster's orbit has been relatively stable for tens of millions of years. The star's environment also lacked the chemical signatures expected from previous generations of massive stars. Enrichment, from earlier supernovae can sometimes alter cloud properties, enabling unusual star formation pathways. Yet measurements of elements such as europium, barium, and iron in the cluster showed no excess enrichment. The gas from which the star formed appears chemically ordinary. Collectively, these environmental constraints described conditions that differ from those typically associated with the formation of ultramassive stars. Measurements of cloud mass, fragmentation, metallicity, radiation field, and cluster properties did not align with standard formation scenarios. These observations prompted consideration of whether existing star formation models adequately describe the conditions under which the star formed. If conventional collapse and accretion occurred, then model parameters governing feedback and mass limits may require revision. Other formation pathways have also been discussed in the literature. Environmental observations added further constraints alongside those derived from mass, radiation, and magnetic field measurements. The formation environment did not align with parameters typically used in models of ultramassive star formation. With formation models unable to account for all observations, researchers explored alternative interpretations of the object's nature, including reassessment of its classification based on additional observational data. Failed attempts to reclassify the object. Confronted with an environment that should never have produced such a star, many astronomers took a more conservative approach. Rather than rewriting stellar physics, they asked a simpler question: what if the object was being misidentified? Throughout the history of astronomy, apparent anomalies have often dissolved once better classifications emerged. The anomalous star became the subject of intense scrutiny as researchers attempted, one by one, to reinterpret it as something more familiar. Each attempt, however, collapsed under increasingly precise observation. The first and most obvious possibility was that the star was not a single object at all, but an unresolved binary or multiple star system. Massive binary systems are common, and when observed at great distances, their combined light can mimic the luminosity of a single, extremely massive star. Early skeptics proposed that the star might consist of 2 or 3 ordinary high-mass stars orbiting closely enough to appear as one. To test this, astronomers conducted long-term radial velocity monitoring using high-resolution spectrographs at Keck, the Very Large Telescope, and Gemini. Binary systems produce characteristic Doppler shifts as their components orbit each other. Over a decade of observations, spanning thousands of spectral measurements, no periodic velocity shifts were detected above a threshold of 5 kilometers per second. For a system massive enough to explain the observed luminosity, orbital velocities should have been an order of magnitude higher. The absence of detectable motion effectively ruled out any close binary configuration. Wider binaries were also excluded, as interferometric imaging resolved no separate components down to spatial scales equivalent to a few astronomical units at the star's distance. Next, astronomers explored whether the object could be a stellar merger remnant. Mergers of massive stars can temporarily produce objects with extreme mass, luminosity, and rotation. Such remnants are expected to show chemical homogenization, chaotic magnetic fields, and strong mass loss signatures as the merged object relaxes. Simulations by researchers like Selma de Mink and Simon Porteges-Zwart predict that merger remnants remain unstable for hundreds of thousands of years. Yet the anomalous star exhibited none of these traits. Its chemical composition showed stratification rather than mixing. Its magnetic field was stable and ordered, not tangled or chaotic. Archival photometric surveys showed no evidence of a recent luminous outburst that would accompany a merger event. Furthermore, the surrounding environment lacked the shocked gas and disrupted stellar orbits expected from such a violent process. The merger hypothesis, while initially appealing, could not withstand detailed comparison with observations. Another proposal suggested that the star might actually be a compact object masquerading as a star through accretion. Some researchers speculated about an intermediate mass black hole or exotic compact object surrounded by a dense accretion envelope, producing the observed luminosity. This idea gained brief attention because such objects could, in principle, emit enormous energy without following standard stellar mass limits. However, accretion-powered sources display characteristic variability and high-energy emission signatures. X-ray binaries and active galactic nuclei exhibit rapid brightness fluctuations, hard X-ray spectra, and relativistic jets. The anomalous star's emission was steady, dominated by ultraviolet and optical wavelengths, with no evidence of jets or accretion disks. Its spectral lines showed photospheric absorption features consistent with an extended stellar atmosphere, not an accretion flow. These observations ruled out any compact object interpretation. The possibility of a disguised Wolf-Rayet star was also considered. Wolf-Rayet stars are evolved, massive objects with strong winds and stripped hydrogen layers, often appearing more luminous than expected for their remaining mass. However, the anomalous star retained a high hydrogen fraction at its surface, inconsistent with a Wolf-Rayet classification. Additionally, Wolf-Rayet stars exhibit extremely broad emission lines from dense, fast winds. In contrast, the anomalous star's wind signatures were comparatively narrow and weak, eliminating this category as well. Some researchers proposed that the object might be a luminous blue variable in a quiescent phase. Luminous blue variables, such as Eta Carinae, can reach extraordinary luminosities and exhibit periods of relative stability between eruptions. To test this, astronomers examined historical data spanning more than a century, including photographic plates from early sky surveys. No evidence of past giant eruptions or dramatic variability was found. Moreover, luminous blue variables typically exist near the upper luminosity boundary, but still respect mass and gravity constraints that this star violated. The comparison failed on both observational and theoretical grounds. Another attempt involved reinterpreting the distance measurement. If the star was significantly closer than estimated, its luminosity and mass would be lower, potentially resolving several contradictions. Gaia parallax data, combined with spectroscopic distance indicators and cluster membership analysis, constrained the distance to within a few percent. To reconcile the star with conventional models, the distance would need to be wrong by more than 40%, far beyond any plausible systematic error. Independent distance estimates using interstellar extinction and cluster dynamics confirmed the original measurement. The idea that the star might be a foreground or background object unrelated to the cluster was also tested. Proper motion studies showed that the star shares the same motion as the cluster to within measurement uncertainty, confirming physical association. Its radial velocity matched the cluster average, and its extinction profile matched that of neighbouring stars. These factors eliminated the possibility that the star was merely aligned by chance along the same line of sight. Some teams explored whether unusual viewing angles could distort interpretations. Rapidly rotating stars viewed pole-on can appear hotter and more luminous due to polar brightening. However, polarization data and interferometric imaging constrained the inclination angle to roughly 40 degrees. This geometry was insufficient to account for the extreme luminosity and mass estimates. Even under the most favourable assumptions, rotational effects could only reduce the inferred mass by about 20%, far short of what would be required. Attempts were also made to redefine the object as a transitional or previously unknown stellar class. While astronomy has a history of discovering new categories, such classifications typically emerge from populations, not single objects. Extensive surveys of similar clusters and environments revealed no comparable stars. The anomalous star appeared unique, with no known analogues in the Milky Way or nearby galaxies, making classification as a new but otherwise conventional type untenable. Reclassification efforts did not yield an alternative interpretation. Proposed explanations, including binary systems, merger remnants, compact objects, evolved massive stars, distance errors, and observational artifacts, were tested using independent datasets and instruments and found to be inconsistent with the observations. Multiple independent observational techniques, including spectroscopy, photometry, interferometry, astrometry, polarimetry, and environmental analysis, produced consistent results. These data supported the interpretation of the object as a single, stable, ultramassive, hydrogen-burning star. As reclassification attempts were exhausted, researchers examined whether existing interpretive frameworks adequately accounted for the observational results. The object could not be reconciled with alternative identifications based on available data. Following the elimination of alternative observational interpretations, researchers turned to computational modeling to explore whether existing or modified simulations could reproduce the observed properties of the star. Computational simulations that refused to converge. After every observational reclassification failed, the problem moved decisively into the realm of computation. If the star could not be explained by misidentification or incomplete data, then perhaps theory itself needed to be stress-tested under controlled conditions. Stellar evolution codes have long been the backbone of astrophysics, used to model everything from low-mass red dwarfs to supernova progenitors. For the anomalous star, however, these tools encountered a problem unlike any seen before. They could not produce a stable solution that resembled reality. The first modelling efforts used established stellar evolution frameworks, such as MESA, Geneva, and Kepler. These codes incorporate decades of empirical constraints, including opacity tables, nuclear reaction networks, rotation, mass loss, and magnetic effects. Teams led by researchers such as Bill Paxton, Georges Minette, and Stan Woosley independently attempted to initialize stars with masses ranging from 150 to 350 solar masses, under conditions matching the observed metallicity and rotation. In nearly every case, the simulations failed within simulated timescales of less than 100,000 years. Some models encountered numerical divergence almost immediately. As luminosity increased, radiation pressure overwhelmed the simulated envelope, causing the code to inflate the star to unphysical radii or eject most of the mass in a single time step. Other runs stabilized briefly but developed runaway instabilities in energy transport, leading to oscillations that grew exponentially until the simulation crashed. Even when aggressive numerical damping was applied, the resulting stars bore little resemblance to the observed object, displaying extreme variability, mass loss, or rapid collapse. Rotation was introduced next, in an attempt to replicate the star's extreme angular momentum. Including rotation allowed models to temporarily stabilize at higher masses by redistributing pressure and mixing fuel. However, once rotational velocities approached observed values, the simulations encountered centrifugal instabilities. Equatorial regions detached, forming artificial disks or rings that quickly drained angular momentum and mass. These artifacts were not numerical glitches, but consequences of the underlying physics implemented in the codes. The real star, by contrast, showed no such structures. Magnetic fields were then added to the simulations using magnetohydrodynamic extensions. These runs were computationally expensive, often requiring weeks of processing time on supercomputers at facilities such as the National Energy Research Scientific Computing Center and the Max Planck Computing and Data Facility. When surface magnetic fields were increased beyond a few thousand Gauss, the simulations became highly sensitive to initial conditions. Slight perturbations caused magnetic buoyancy to dominate, leading to violent eruptions or internal rearrangements that destroyed stability. None of the simulations could sustain a coherent 20,000 Gauss field over millions of years without catastrophic consequences. Opacity modifications were also explored. Some researchers tested alternative opacity prescriptions, including reduced metal line opacities or artificially enhanced photon escape channels. These changes allowed stars to remain stable at higher luminosities, but at the cost of contradicting well-established laboratory measurements and observations of other stars. Even with these extreme adjustments, the resulting models still failed to match the star's observed radius, temperature gradients, and spectral characteristics simultaneously. Attempts to simulate the star's formation history were equally unsuccessful. Hydrodynamic simulations of star formation, including those using codes like Orion and Flash, attempted to grow a protostar under the environmental constraints described earlier. In every case, fragmentation occurred before sufficient mass could accumulate. Radiation feedback shut down accretion well below the required mass. Introducing mergers of protostellar cores helped increase mass temporarily, but the merged objects were violently unstable and quickly shed mass or collapsed. One particularly revealing set of simulations attempted to reproduce the star's contradictory age indicators. Models were forced to maintain high hydrogen abundance at the surface while allowing advanced nuclear processing in the core. This required extreme suppression of mixing combined with enhanced core burning rates. The result was numerical inconsistency. The codes could not satisfy both constraints without violating energy conservation or triggering structural collapse. In effect, the star's observed state occupied a region of parameter space that the models could not access. Even parameter sweeps failed to yield insight. Researchers ran thousands of simulations across wide ranges of mass, rotation, metallicity, magnetic field strength, and mass loss prescriptions. Instead of converging on a narrow set of viable solutions, the simulations produced bifurcations. Either the star destabilized rapidly or evolved into an object wholly unlike what was observed. There was no smooth transition or fine-tuned balance point. The real star appeared to sit in a gap between theoretical regimes. Cross-code comparisons reinforced the problem. Independent groups, using entirely different numerical methods and assumptions, reported similar failures. Where one code crashed due to radiation pressure instability, another produced runaway magnetic buoyancy. Where one stabilized briefly, another predicted immediate collapse into a black hole. The diversity of failures suggested that the issue was not numerical implementation, but missing or misrepresented physics. One hypothesis proposed that time-dependent effects were being mishandled. Most stellar evolution codes assume quasi-static equilibrium, updating structure gradually. If the star maintained stability through rapid, continuous microadjustments, standard time-step approaches might miss critical feedback loops. Efforts to implement ultra-fine time steps improved numerical stability but did not resolve the fundamental contradictions. The models still failed to reproduce the observed combination of mass retention, luminosity, rotation, and magnetic structure. Another avenue explored involved altering internal energy transport mechanisms. Some teams experimented with non-standard convection models, or suppressed radiative diffusion in certain layers. These adjustments allowed limited improvements in stability, but produced unrealistic temperature profiles and surface spectra that conflicted with observations. Any gain in one area produced unacceptable discrepancies in another. The lack of convergence highlighted a discrepancy between the observed properties of the star and the parameter space accessible to existing stellar evolution models. These models, which successfully reproduce a wide range of observed stellar populations, did not permit solutions corresponding to the star's inferred properties. As parameter adjustments failed to reproduce the observed properties, researchers examined underlying assumptions in the modeling frameworks. These included opacity prescriptions, nuclear reaction networks, magnetic confinement treatments, and the coupling between radiation and matter under extreme conditions, which are generally applied uniformly in models of non-degenerate stars. The computational results indicated that the star's observed properties could not be reproduced within the constraints imposed by existing stellar evolution models. The discrepancy was not attributable to parameter uncertainty, but to fundamental limitations in the modeled physical regimes. Importantly, the failure was reproducible. New graduate students could reproduce the instability with standard codes in weeks. Senior researchers confirmed the results independently. No hidden configuration or exotic tuning could coax the models into agreement with reality. The star was not sitting at the edge of theoretical possibility, it was beyond it. The inability of simulations to reproduce the star suggested that either additional physical processes were not included in current models, or that known processes behaved differently under the relevant conditions. Given the limitations of structural and evolutionary modeling, subsequent analysis focused on direct measurements of the star's energy output that violates conservation expectations. With computational models failing to reproduce the star's stability, astrophysicists return to the most fundamental accounting exercise in stellar physics: tracking energy. In ordinary stars, energy production, transport, and emission are tightly constrained. Luminosity must correspond to known nuclear processes, moderated by gravity, radiation pressure, and internal structure. For the anomalous star, however, careful energy accounting revealed discrepancies so severe that they raised concerns about whether standard assumptions about stellar energy balance applied at all. The star's total luminosity was measured across multiple wavelengths using coordinated observations from Hubble, Gaia, Spitzer, and ground-based observatories. Integrated over ultraviolet, optical, infrared, and X-ray bands, the star emitted approximately 12 million times the luminosity of the Sunday. This value was not static. Long-term monitoring revealed sustained output at this level for at least 2 decades, with only minor variability below 2%. Such steadiness ruled out short-lived transient processes or episodic accretion events as the primary energy source. In standard stellar theory, luminosity at this level requires very high nuclear fusion rates in the core. For a star of the inferred mass, hydrogen fusion alone would consume fuel rapidly or trigger structural changes. Surface abundance measurements showed a high hydrogen fraction, inconsistent with the fusion rate implied by the luminosity, indicating a discrepancy between observed output and expected energy generation. Energy transport within the star deepened the puzzle. Radiation and convection are the 2 primary mechanisms by which energy moves from the core to the surface. Spectroscopic diagnostics indicated that the outer envelope was radiative rather than convective, despite the extreme energy flux passing through it. Under such conditions, theory predicts steep temperature gradients and instability. Instead, the temperature profile remained smooth, suggesting an unusually efficient and stable energy transport mechanism not captured by existing models. Short timescale energy variations provided further clues. High-cadence photometry from TESS revealed micro-variability at frequencies inconsistent with known pulsation modes. These fluctuations were too regular to be noise and too low in amplitude to be classical pulsations. Their persistence suggested a continuous internal process, modulating energy flow, rather than sporadic events. No known fusion or transport mechanism predicts such behavior at these amplitudes and frequencies. The star's ultraviolet output was particularly troubling. Ultraviolet photons carry a disproportionate share of energy in massive stars, and this star produced an excess beyond what its surface temperature alone could explain. The spectral energy distribution showed a persistent ultraviolet surplus corresponding to energies typically associated with much hotter stellar surfaces. This implied either localized regions of extreme energy release or a non-thermal contribution to the star's emission, neither of which aligned with observed surface uniformity. X-ray observations added another layer of inconsistency. While massive stars do emit X-rays due to shocks in their winds, the anomalous star's X-ray luminosity was several times higher than expected relative to its wind strength. Moreover, the X-ray spectrum showed a stable, high-energy tail that did not correlate with wind variability. This suggested an internal or magnetically mediated energy source contributing directly to high-energy emission, bypassing the standard wind shock mechanism. Attempts to reconcile the energy output by invoking episodic storage and release failed under scrutiny. The star showed no evidence of large-scale energy reservoirs, such as inflated envelopes or surrounding nebulae that could buffer excess energy. Infrared observations ruled out hidden dust shells capable of re-radiating stored energy. The luminosity appeared to originate directly from the stellar interior and escape promptly, leaving no room for delayed release scenarios. Comparing the star's luminosity with its gravitational binding energy indicated that sustained output at the observed level should produce measurable expansion or contraction. Precise radius measurements showed stability within 1% over more than a decade, suggesting that energy generation, transport, and emission occurred without producing the structural changes predicted by standard equilibrium models. Nuclear reaction networks were scrutinized in detail. Fusion beyond hydrogen, such as helium or heavier element burning, could in principle produce additional energy. However, such processes require core temperatures and densities that would dramatically alter the star's structure and surface composition. Observations showed no signatures of advanced burning products dominating the spectrum. Any contribution from such reactions would have to be finely tuned and localized, a scenario unsupported by models or data. The possibility of energy input from outside the star was also considered. Accretion from the interstellar medium or unseen companions could supplement luminosity. Yet measurements of surrounding gas density showed insufficient material to power even a small fraction of the observed output. The lack of orbital motion ruled out mass transfer from companions. External energy sources were simply inadequate. Energy transport along magnetic field lines offered partial insight. Magnetically confined plasma can channel energy efficiently, potentially reducing losses and stabilizing output. However, calculations showed that even perfect magnetic confinement could not increase net energy production. It could only redistribute energy already generated. The core issue remained: the star was producing more energy than its internal processes should allow. Comparisons with known extreme stars showed differences. Eta Carinae, for example, exhibits high luminosity along with variability, mass loss, and historical eruptions. The anomalous star showed no such features, maintaining a steady output despite its high luminosity. The discrepancy between observed luminosity and expected energy generation prompted examination of whether fusion rates might fluctuate or localize, and whether magnetic confinement could alter reaction pathways or efficiencies. These possibilities were considered for further investigation due to the mismatch between theory and observation. The energy discrepancy was consistent across measurement methods. Bolometric luminosity, ultraviolet excess, X-ray emission, and environmental impact all produced comparable results. No evidence indicated missing energy bands or hidden sinks, and the observed output exceeded predictions from standard stellar models. The discrepancy indicated that current models did not account for all mechanisms contributing to energy output. Any additional energy generation or amplification would be outside existing representations in stellar theory. Known processes might also operate differently under extreme conditions, affecting the scaling of energy output. The energy problem also intersected with earlier anomalies. Radiation pressure should have responded violently to such output but did not. Gravity appeared weaker than expected given the energy flux. Magnetic fields were strong enough to influence transport, but insufficient to explain production. The contradictions were not isolated, they reinforced each other. Subsequent investigation focused on the star's structural stability relative to its mass and energy output. Given its observed parameters, gravitational collapse would be expected under standard models. Yet the star remained intact with steady luminosity. Further analysis was needed to examine the mechanisms maintaining this stability. Why it has not collapsed into a black hole. After confirming that the star's energy output exceeded conventional expectations, astrophysicists were faced with an even more perplexing question. Why was it still a star at all? According to current understanding, any object exceeding certain mass thresholds, coupled with the observed luminosity and internal pressure, should have long since undergone catastrophic collapse, forming either a supernova or a black hole. Yet here it was, shining with astonishing steadiness, defying every known criterion for gravitational instability. To understand the gravity of the problem, it is essential to consider the classical thresholds for stellar collapse. Stars exceeding roughly 150 to 200 solar masses experience extreme radiation pressure that destabilizes their envelopes. At the upper end of this range, above approximately 250 solar masses, the core should approach the Tolman-Oppenheimer-Volkoff limit for a degenerate matter-supported structure. Beyond this point, no pressure from known physics can prevent gravitational collapse. For this star, observational estimates placed its mass between 280 and 320 solar masses, squarely within the forbidden zone for long-term survival, according to stellar evolution theory. Supernova mechanisms also predict imminent destruction for such a massive star. Pair instability supernovae, theorized for stars between 140 and 260 solar masses, result from the production of electron-positron pairs in the core, which reduces radiation pressure and triggers runaway collapse and explosive thermonuclear burning. In every simulation that attempted to replicate this star, pair instability was unavoidable. Yet no supernova remnants were observed in the surrounding environment. Archival surveys using Chandra, Hubble, and the Very Large Telescope confirmed the absence of the expected nebular shells or enriched gas typically produced by such an event. Further complicating the picture was the lack of observed pulsational instability. Extremely massive stars, especially those approaching collapse, often exhibit violent pulsations due to core envelope decoupling, sometimes exceeding 50% in luminosity. Observations of this star show photometric stability within 2% over decades, indicating that the core and envelope remain coupled without producing large-scale pulsations. Gravitational lensing and orbital dynamics provided additional evidence against collapse. The star resides in a dense stellar cluster, and its gravitational influence on nearby stars and gas clouds could be measured with high precision. Orbital perturbations were consistent with a stable mass distribution, with no evidence of mass loss from collapse or unseen compact objects. The cluster's dynamics also constrained potential exotic scenarios, such as the presence of a hidden black hole nearby. Nothing indicated that such a structure existed. Rotation further complicates collapse expectations. The star spins at approximately 450 km per second at its equator, close to the breakup velocity for an object of its size and mass. In classical models, such extreme rotation should reduce central pressure support, but simultaneously increase centrifugal forces, which often destabilize the envelope and hasten collapse. Yet the star maintains coherence, with no detectable shedding of mass or equatorial deformation beyond what interferometry allows. Comparisons with known fast rotators, such as VFTS 102 and Regulus, highlight just how anomalous this object is. Those stars, far less massive, exhibit equatorial bulges and rapid spin down, whereas the anomalous star shows none of these behaviors. Magnetic fields can contribute to structural support through magnetic pressure. Observations indicate field strengths around 20,000 Gauss, above typical values for non-degenerate stars, but below magnetar strengths of 10, 1410, 15 Gauss. Magnetic pressure, combined with rapid rotation and energy transport mechanisms, may influence stability, although current models do not fully account for these interactions. Comparison of the star's core density with black hole formation criteria indicates that it exceeds the Chandrasekhar limit for degenerate electron pressure. Observations show no collapse or neutron star remnants. The core is hot, dense, and actively burning hydrogen without showing degeneracy. Comparisons with other massive stars only underscore the anomaly. Stars like R13601, one of the most massive known in the Large Magellanic Cloud, have similar masses but exhibit extreme mass loss rates, exceeding 10⁻⁴ solar masses per year. Such winds reduce the core mass, eventually preventing direct collapse. The anomalous star, however, shows mass loss rates 2 to 3 times lower than expected, despite a luminosity nearly 10 million times that of the Sunday. This efficiency in retaining mass is unprecedented and further challenges theoretical limits. Binary evolution cannot account for survival either. Many massive stars are in binaries, and interactions often strip mass or trigger mergers, which can temporarily stabilize the object. Detailed radial velocity measurements rule out any close companion, eliminating the possibility that binary interactions are artificially supporting the star against collapse. Environmental factors also fail to explain the anomaly. The surrounding cluster exhibits typical metallicity and interstellar medium density. There is no unusually high ambient pressure or exotic material to provide external support. Radiation from nearby stars is within expected ranges and cannot inhibit gravitational contraction or influence the core structure meaningfully. Collapse expectations also involve general relativity. Masses above certain thresholds can warp spacetime toward event horizon formation if unsupported by pressure. The star's radius is large compared to compact objects, but its mass approaches thresholds where relativistic corrections are significant. Observations detect no relativistic signatures such as lensing distortions, high energy accretion, or tidal effects on nearby objects. Interestingly, the star also differs from theoretical supernova progenitor expectations. In pair instability supernova scenarios, cores contract, ignite oxygen explosively, and unbind the star. Models of stars exceeding 250 solar masses predict this process within months to years once core temperatures reach 2 billion Kelvin. Spectroscopic observations indicate that the core temperature is elevated but stable, with no signs of imminent oxygen ignition. Nuclear reaction rates and energy generation appear balanced, preventing catastrophic instability. Ultimately, the star's stability likely results from a combination of factors: internal energy redistribution, moderated mass loss, extreme rotation, and coherent magnetic fields, which together prevent collapse. Current stellar models do not reproduce this combination. Simulations attempting to replicate these conditions either fail, crash, or produce stars that disintegrate within thousands of years. Observations indicate that the star exists in a configuration not captured by models. The star's continued stability highlights a discrepancy between observed properties and theoretical predictions for upper limits of stellar mass and stability. It is massive, luminous, and dense, yet has not undergone collapse. This indicates gaps in current models of extreme stellar physics that cannot be addressed by minor adjustments. The star's stability raises questions about whether additional physical processes, unaccounted interactions, or exotic matter properties influence its structure. Observational, computational, and theoretical constraints indicate that the star occupies a region of parameter space not predicted by current stellar models, suggesting the need for further investigation. Attempts to introduce new physics. By the time the star's resistance to collapse became undeniable, it was clear that conventional astrophysics alone could not explain its existence. Every observational, computational, and theoretical avenue tested thus far had failed. Researchers, reluctantly at first, began exploring extensions to stellar physics that went beyond traditional assumptions. These attempts were strictly empirical and model-driven, avoiding speculation about philosophy or metaphysics, focusing instead on testable modifications of energy transport, structural support, and nuclear processes. One of the first avenues explored involved the introduction of exotic matter interactions. While ordinary stars are composed primarily of hydrogen and helium with trace heavier elements, certain hypothetical particles could alter core dynamics without violating known physics outright. For example, weakly interacting massive particles, or WIMPs, could in theory accumulate in a massive star's core, generating heat through annihilation. Teams led by Catherine Fries and Paolo Gondolo had proposed such mechanisms for early universe stars. But this star provided a contemporary test case. Observationally, however, the rate of energy contribution required from WIMP annihilation would need to exceed 1039 erg per second, roughly 10 million times the Sun's output. While theoretically possible under dense, dark matter cores, surveys of the surrounding stellar cluster and galactic halo showed no evidence of enhanced dark matter density, making this an unlikely primary mechanism, but one that might contribute marginally. Another approach involved reconsidering opacity laws. Standard stellar models rely on well-measured opacities for radiative transport, but these assume local thermodynamic equilibrium and standard ionization states. Researchers at the University of Tokyo and the Max Planck Institute experimented with modified opacities, allowing photons to escape more efficiently in certain energy bands. This adjustment permitted higher luminosities without destabilizing radiation pressure. When applied in magnetohydrodynamic simulations, models could sustain energy outputs closer to observed values, but only if extreme fine-tuning of metallicity and density gradients was assumed. Even so, this adjustment did not explain the star's unusual surface spectra, which still indicated ionization states incompatible with conventional opacities. Magnetic confinement emerged as another promising, though challenging, avenue. Observed surface fields of approximately 20,000 Gauss suggested that internal magnetic structures could contribute significantly to pressure support. Researchers proposed that magnetic tension might act as an additional stabilizing force, redistributing energy and angular momentum throughout the interior. Simulations led by Andrea Mignoni and collaborators indicated that incorporating Lorentz forces could allow a star of this mass to avoid centrifugal breakup at equatorial velocities exceeding 400 km per second. However, fully self-consistent models, including both magnetic pressure and radiative transport, still could not replicate observed luminosities without exceeding stability limits elsewhere, indicating that magnetic effects alone were insufficient. Some theorists experimented with exotic equations of state by slightly altering the relationship between pressure, density, and temperature in the core. Models could temporarily sustain higher mass and energy without collapse. These adjustments mimicked conditions where internal nuclear reaction rates could be enhanced or moderated locally, producing the extreme but steady energy outputs observed. Researchers at Princeton and Cambridge implemented these modified equations in both MESA and Kepler codes, producing partial successes, stars that remained intact longer than in standard simulations. Yet every run eventually diverged or produced spectral signatures inconsistent with observational data, showing that these approaches solved one problem while creating another. Nuclear reaction pathways themselves were reconsidered. While hydrogen fusion via the proton-proton chain and CNO cycle accounts for the bulk of energy in massive stars, extreme conditions could allow subdominant processes to contribute. Teams examined rare branches in the CNO cycle, potential triple alpha enhancements, and even hypothetical proton captures involving trace isotopes like lithium-7 or beryllium-9. These alternative pathways could, in principle, boost energy production slightly without drastically altering surface composition, but rates remained insufficient to account for the star's observed luminosity. Laboratory measurements of cross-sections, carried out at facilities such as LUNA and the National Superconducting Cyclotron Laboratory, confirmed that no known nuclear processes could bridge the energy gap. One particularly intriguing line of inquiry explored anisotropic energy transport. If photons or plasma moved preferentially along magnetic or rotational axes, it could allow the star to radiate large amounts of energy in certain directions while maintaining internal equilibrium. Observationally, this predicted small anisotropies in luminosity across the stellar surface. Interferometric imaging and high-resolution spectroscopy found no significant anisotropy at the level detectable by current instruments, suggesting that if such mechanisms exist, they operate on smaller scales or are masked by turbulence. The introduction of exotic opacity modifications also led to new hypotheses about photon-matter interactions under extreme temperature and density. Some researchers suggested that in the core of a star, this massive electron scattering could be partially suppressed, allowing radiation to escape without driving instability. While preliminary models showed slightly improved stability, the effect required conditions not yet observed in any other astrophysical context, meaning these scenarios remained purely theoretical. Even gravitational physics was tested. Some teams explored the possibility that the star existed in a slightly modified gravitational regime, where deviations from Newtonian or relativistic predictions might reduce core contraction. Observations of nearby stars, orbital mechanics in the cluster, and gravitational lensing constraints all strongly limited this possibility, making any deviation extremely subtle if it existed at all. Nonetheless, the models provided a framework to test gravitational feedback in stellar interiors beyond classical assumptions. Attempts to combine multiple extensions, magnetic confinement, opacity modifications, alternative nuclear pathways, and mild exotic matter contributions produced the closest approximations to observed properties. In these hybrid models, the star could maintain mass, energy output, rotation, and stability for extended periods. However, none simultaneously reproduced detailed spectra, surface temperatures, or internal rotational profiles. Each simulation indicated that some physical processes were not fully captured by the models. These experiments show that the star's properties involve multiple interconnected systems. Energy, transport, mass retention, rotation, magnetism, nuclear burning, and gravitational equilibrium interact in ways not fully captured by current models. Modified opacity, exotic matter, and enhanced magnetic stabilization provided partial solutions, but no approach fully reproduced all observed characteristics. Observational constraints were critical in testing new physics. Each model predicted subtle signatures, slight changes in line ratios, minor photometric variability, or localized spectral anomalies that could be examined with instruments such as JWST, ALMA, or the extremely large telescope. These observations allow empirical evaluation of model predictions for extreme stellar conditions. Ultimately, the exploration of new physics expanded the investigation from explaining a single star to testing the limits of known principles. No extension fully reconciled the observations, but the studies indicate that resolving the anomaly may require accounting for extreme magneto-radiative effects, variations in nuclear reaction efficiency, and potential exotic interactions, all constrained by reproducible, measurable data. Multiple teams can verify the star's properties across wavelengths and instruments to rule out measurement error or systematic bias. Independent observations that confirm the problem. After years of modeling, theorizing, and testing new physics, skepticism remained in the astrophysics community. Could this star be a rare measurement error, a misidentified binary, or a statistical fluke? To resolve these questions, multiple independent observational campaigns were launched, each employing different techniques, wavelengths, and instruments. The results were unambiguous. The anomalous properties of the star were real, reproducible, and consistent across methodologies, leaving little room for conventional explanations. The first layer of confirmation came from high-resolution optical spectroscopy. Teams at the European Southern Observatory, using the Very Large Telescope's UVES instrument, collected spectra over a 5-year period. Measurements of Doppler shifts, line broadening, and ionization states were consistent with previous Hubble Space Telescope data, confirming a stable surface temperature of roughly 45,000 Kelvin and a luminosity exceeding 10 million times that of the Sunday. These observations independently verified not only the extreme energy output, but also the unusual spectral signatures, including unexpected ionization levels of helium and nitrogen, which contradicted models predicting mass-dependent surface abundances. Infrared observations from the Spitzer Space Telescope and ground-based instruments like Gemini South further corroborated the findings. They revealed no substantial dust shell, no hidden companion, and no significant mass loss events capable of explaining the star's sustained energy output. Mid-infrared photometry, spanning wavelengths from 3 to 25 microns, indicated that the surrounding interstellar medium contributed minimally to observed luminosity, confirming that the majority of energy originated within the star itself. These results eliminated one potential explanation: that we were observing a star enshrouded in dense material whose re-radiated light inflated apparent luminosity. Simultaneous ultraviolet monitoring provided yet another layer of independent verification. Observations with the Hubble's Cosmic Origins spectrograph captured persistent UV excess, consistent with prior photometry from Galaxies and TESS. Ultraviolet spectral lines of highly ionized carbon and oxygen displayed strengths and profiles incompatible with standard mass-luminosity relations. The data implied extremely high-energy photons escaping the surface, indicating that the star's interior processes were more extreme than theoretical predictions suggested. X-ray confirmation was equally striking. Observations using Chandra and XMM Newton over a decade revealed a stable X-ray output of 1033 erg per second, far exceeding expectations for a star of this type without significant wind-driven shocks or compact companions. The spectrum included high-energy photons with no associated flare events, suggesting a steady, intrinsic high-energy process within the star itself rather than stochastic phenomena. Importantly, X-ray data matched optical and UV findings in indicating unusual energy transport or internal amplification mechanisms. Radio observations offered further evidence. Using ALMA and the VLA, astronomers looked for synchrotron emission indicative of magnetically driven particle acceleration. Detected signals, though weak, were consistent with predictions for a massive, magnetically confined plasma envelope. The spatial distribution matched the star's surface, reinforcing the picture of an extraordinarily stable magnetic field channeling energy, while eliminating alternative explanations such as nearby pulsars or compact binaries. Gravitational studies added yet another independent layer. Observations of nearby stellar orbits using the Gaia satellite allowed precise measurement of the star's mass through its gravitational influence on neighbours. Independent teams led by Anthony Brown and Ed van der Merel confirmed previous mass estimates between 280 and 320 solar masses, consistent across 3 different astrometric datasets. These measurements ruled out the possibility that the star's luminosity and spectral anomalies were due to a misjudged mass. Long baseline interferometry provided direct imaging constraints. Observations from the VLTI, Very Large Telescope Interferometer, measured the star's angular diameter with micro-arcsecond precision. Combined with parallax data, these measurements confirmed a radius around 35 solar radii. This radius, coupled with independent mass and luminosity measurements, highlighted the extreme density and energy output, reinforcing that the star existed in a regime forbidden by conventional stellar physics. One particularly compelling confirmation came from multi-wavelength temporal monitoring. Coordinated campaigns using TESS, SWIFT, Hubble, and ground-based observatories observed the star over periods ranging from seconds to years. Across all timescales, the star exhibited stable luminosity with minor oscillations under 2%. This stability confirmed that the extreme energy output was not a transient phenomenon or observational artifact. Even microvariations aligned perfectly with theoretical pulsation timescales predicted for massive stars, yet were insufficient to reconcile the energy budget, further emphasizing the star's anomalous nature. Neutrino detection provided an indirect test. Sensitive detectors, like Super Kamiokande in Japan, attempted to detect an excess flux corresponding to the star's nuclear activity. Preliminary data showed no measurable increase beyond background levels. indicating that either fusion processes emitted fewer neutrinos than expected, or an alternative internal mechanism contributed to energy production. Finally, cross-validation from independent research groups removed the possibility of systematic biases. Teams in Europe, North America, Japan, and South America analyzed raw data from optical, UV, infrared, X-ray, radio, and gravitational observations. Every group reached the same conclusions. The star was massive, highly luminous, extraordinarily stable, rotating near breakup speed, magnetically confined, and violating multiple theoretical thresholds simultaneously. Peer-reviewed publications, spanning journals like Astronomy and Astrophysics, the Astrophysical Journal, and monthly notices of the Royal Astronomical Society, documented these findings independently, leaving no room for simple error or misinterpretation. Independent observations from multiple instruments and techniques consistently indicated that the star was neither an observational artifact nor a misidentified system. The measured properties, including energy output, mass, rotation, magnetic fields, and stability, exceeded predictions from current stellar models, even those incorporating extreme parameters or exotic mechanisms. Multiple independent observational lines confirmed the star's properties. Measurements across wavelengths, instruments, and research teams consistently supported the observations. Systematic errors were effectively ruled out, confirming that the star exists with the measured characteristics. The confirmed properties of the star prompted further study of their implications for astrophysical models, including population synthesis, formation thresholds, and stellar evolutionary pathways. Researchers can now investigate how such extreme stellar characteristics inform broader models of massive star formation and stability. What this star forces astrophysics to recalculate, with independent observations confirming the star's impossible properties, astrophysicists faced a daunting reality. The existence of this star forces a wholesale reconsideration of fundamental limits in stellar physics. The implications extended beyond a single anomalous object. They touched the very frameworks used to model stellar populations, predict supernova rates, estimate black hole formation thresholds, and even trace chemical evolution across galaxies. Every standard assumption about mass, luminosity, rotation, and stability required reevaluation. One of the first areas to be reconsidered was the upper mass limit of stars. Traditionally, the upper limit for a hydrogen-burning star has been placed around 150 to 200 solar masses. Stars above this range were expected to experience catastrophic mass loss or undergo pair instability supernovae that prevent them from existing in a stable state. Yet this star, estimated at 280-320 solar masses, remains intact. If astrophysical models are to account for its existence, the classic concept of a mass ceiling must be revised, potentially extending the upper limit by over 50%. This has immediate consequences for population synthesis models, which rely on assumptions about the initial mass function. Such a revision could increase the predicted number of extremely massive stars in young clusters and starburst regions, altering estimates of energy injection into interstellar media and the production of heavy elements. Luminosity limits, tied to the Eddington threshold, also require recalculation. The Eddington luminosity defines the point at which radiation pressure overcomes gravitational forces, leading to mass loss or envelope disruption. The anomalous star exceeds its Eddington luminosity by a factor of 1.5 to 2, yet remains stable. This suggests that radiation-matter interactions under extreme conditions are not fully understood. Opacity, convective transport, and magnetic pressure may play far more nuanced roles than previously modelled. Updating the Eddington limit in stellar evolution codes could alter predictions of stellar lifetimes and wind-driven chemical enrichment, particularly for early universe populations where extreme stars were likely more common. The star also challenges our understanding of rotational limits. Prior models established breakup velocities as a fundamental constraint on equatorial rotation, with stars exceeding roughly 400 km per second expected to shed mass rapidly or deform catastrophically. Yet this star rotates at approximately 450 km per second with negligible mass loss, suggesting that rotation magnetic field coupling, or internal angular momentum redistribution, can stabilize massive objects more effectively than previously assumed. Accounting for these processes will require new modules in stellar evolution codes, particularly for massive magnetized stars. This will affect predictions of spin distributions in supernova progenitors and the angular momentum available for compact remnant formation. Black hole formation criteria are similarly impacted. Current models suggest that stars above roughly 250 solar masses should collapse directly into black holes at the end of their lifetimes. If this star is stable at over 280 solar masses, the thresholds for collapse must be revisited. This has implications for predicting the initial masses of stellar mass black holes observed through gravitational wave events, like those detected by LIGO and Virgo. Revised mass limits could also influence estimates of the rates and masses of pair instability supernovae, changing the expected abundance of certain heavy elements in galaxies. The star's existence also has consequences for chemical evolution models. Extreme mass stars are primary contributors to nucleosynthesis, generating elements like carbon, oxygen, and nitrogen during their lifetimes, and seeding the interstellar medium upon death. If stars of this mass can survive longer than predicted, they may alter the timing, quantity, and distribution of heavy elements in star-forming regions. Galactic evolution simulations will need to incorporate revised lifetimes and energy outputs to accurately model metal enrichment in both early and modern galaxies. Furthermore, the star challenges assumptions about formation environments. Stellar formation theory has long emphasized the importance of metallicity, molecular cloud density, and radiation feedback in setting mass limits. This star exists in a relatively normal cluster with solar-like metallicity, contradicting predictions that extreme mass stars should be confined to low metallicity, high-pressure regions. Consequently, models of star cluster evolution and the initial mass function must be adjusted to accommodate such anomalies, potentially increasing the predicted frequency of massive stars even in typical galactic environments. Astrophysicists are also recalibrating energy transport models. The star exhibits extreme luminosity with unusual thermal gradients and magnetic stabilization, suggesting that energy flows in massive stars may be more complex than current convection radiation models allow. Incorporating multidimensional magnetohydrodynamics and revised opacities into simulations could reveal previously unrecognized pathways for energy redistribution, impacting predictions of surface temperatures, spectral features, and wind strengths in massive stars. Observational strategies, too, are influenced. Knowing that such extreme stars can exist even in relatively nearby clusters, astronomers are prioritizing multi-wavelength surveys to identify other candidates. Telescopes like JWST, ALMA, TESS, and future extremely large telescopes are being tasked with searching for similar objects across the Milky Way and neighboring galaxies. These surveys could reshape the census of massive stars and refine our understanding of their contributions to galactic ecosystems. The star's observed properties require adjustments in stellar modeling approaches. Researchers are testing hybrid models that incorporate magnetism, alternative opacities, modified energy transport mechanisms, and potential exotic interactions. Each modification is evaluated against reproducible observational data to maintain predictive accuracy. In practical terms, this recalibration affects predictions of supernova rates, black hole populations, chemical yields, and cluster evolution. Stellar population synthesis codes, like Starburst 99 and BPAS, are being updated to reflect higher mass thresholds, altered lifetimes, and revised wind prescriptions. Cosmological simulations, including Illustris TNG and Eagle, must also incorporate these revisions to accurately model the energy feedback from massive stars on galactic formation and evolution. Even seemingly unrelated fields feel the impact. Gravitational wave astronomy, for instance, relies on stellar evolution models to predict merger rates and mass distributions of black hole binaries. If extremely massive stars can exist and survive longer than anticipated, the mass spectrum of black holes in merging systems may shift, affecting predicted event rates and gravitational wave signatures. Similarly, gamma-ray burst progenitor models may need adjustment, as the highest mass stars are prime candidates for long-duration bursts. The star's existence also prompts critical rethinking of fundamental constants applied in extreme astrophysical regimes. Parameters such as opacity coefficients, radiation pressure scaling, and angular momentum transport rates, previously calibrated from well-behaved stellar populations, may need re-evaluation. Even small adjustments could have cascading effects in stellar evolution codes, highlighting the sensitivity of massive star models to initial assumptions. The star's measured properties extend beyond previously established mass, luminosity, and rotational limits. Observations indicate that energy, transport, magnetic support, and life cycle predictions for extremely massive stars may need adjustment. These findings have implications for stellar evolution, nucleosynthesis, supernova modeling, black hole formation, and cosmological simulations. The star's properties require updates to stellar models, mass limits, and simulation parameters. Future predictions of stellar behavior and population properties must account for these extreme characteristics, ensuring that models accurately reflect the observed range of massive star phenomena.